this is the, this is the first. We have to thank Ken for all his work to make the space gathering happen. Thank you, Ken. You did great work.
Oh, thank you. Great pleasure. Great pleasure. Sorry for a little bit delay. There are two reasons. One is that we are trying to get more people join before we start. The second reason is I was trying to set up a second camera so people can see the speaker earlier. But anyway, sorry for the delay, but I'll be very quick. So thank you so much for joining us today for the AIAA Los Angeles speaker section. The very special meeting, space architecture gathering with space AIAA Space Architecture Technical Committee and some invited guests from non-SATC members. We have a brilliant lineup of distinguished speakers. They are the leaders in the industry for space architecture. This is a very exciting topic. And as you know, Starship is going to, the Ship 24 is going to attempt to launch it.
Did you hear that? Did you hear that? Starship.
Yeah, 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 and also very good, very good. And we also have the May 11. We also give the excellent award to LJ Rocketdyne for the Artemis 1. So things are keep moving, and we know, and also Gorman and some other company involved in Artemis 2. So things are moving. So this space architecture is getting more and more closer for reality. Of course, the other launch vehicle, other activity as well. Just a brief kind of logistic. First of all, there are coffee, coffee cups and hot coffee in the kitchen there. There's also a kettle for hot water if you want the tea. There's bottled water there, and the restroom is outside. But you might need to wave hand to the librarian because the door is actually locked. They don't want anybody to use it, but if you wave hand to them, they open it for you. And the other thing is because we have speaker lined up, different part of the world, so we don't have a lunch break. But you're welcome to walk outside to grab your lunch. There's a corner burger just right across 30-second to 1 minute walk. You're welcome to bring it and back here to continue to enjoy the food. Around lunchtime, there might be a line, but may not. You can give it a try. If you want other places, you can call in ahead and call for delivery. So that's the basic logistics. So basically today we have 3 sessions, and the first 2 sessions mostly are by the members of SATC, Space Architecture Technical Committee member. Today, the Grand Master Moderator is none other than Professor Madhu Sankapanu. We have 2 co-chairs. One is Sandra, the other is Alma. Sandra is actually the current chair of the Space Architecture Technical Committee. So I will introduce them 3, but I think it's better for them to kind of say a bit more about themselves as well. I'll just one more words about AIAA because this event is hosted by AIAA, and we are the Los Angeles Speaker Section local chapter, but we have the most vibrant activity and aerospace activity in this area that we welcome members, non-members, and we got a lot of advantage being a member. And for example, if you join member, you can join the technical committee like SATC or other technical committee. So our section have been doing our best to bring the AIAA activity to local and domestic and international members. And we actually recruited many members, from France. There are actually 30 students from France and other India, other places. They are just not going to be affiliated with our section because it's counted locally with zip code, but we're more than happy to help the overall AIAA and the aerospace community. So we have an interesting event coming up. So if you look up AIAA.org, that's our national, then you can, Sandra will tell you about this space architecture.org, it's a SATC website. So once in a while, we connect to our AIAA technical committee to make sure people know what AIAA has been doing. AIAA publish and also provide great member services. And but our event and speaker and member non-members are welcome. One more thing is our local chapter website is www.aiaa-lalv.org. So I'm the section chair, and we have wonderful volunteer Mike Nygren on the back helping us, and we have Jeremy, Mr. Jeremy Robert from FAA. He is going to be our career and workforce development chair starting June 1st, pending the election result. So welcome everybody. So so now, sorry, I kind of delayed a little bit, but we will catch up. We can extend a little bit. Don't worry. With this, I first introduced the because Sandra and Alma has been putting a lot of time, of course, Madhu as well. But since we put the title as SATC with AIAA Los Angeles, so first I will introduce Sandra as the chair of the SATC. Then I will introduce Madhu as a grandmaster moderator for the whole day, and Sandra is also the moderator for the panel for the session one and the panel. And Alma is going to. I mean, it depends on. Madhu might have some slight adjustment, so we'll see. So Sandra is a professor in Europe, so I don't want to repeat the same bio that you can see all online. So Sandra, maybe do you want to say a few words about yourself and SATC?
Yes, hello, welcome. I'm very happy that we have succeeded in this grant, Space Architecture Gathering. And I see this really as the first of many others to follow. I am the current chair of the Space Architecture Technical Committee. Thank you for your introduction. And besides that, my home base is at the TU Wien, where I teach architecture, space architecture. And I also have a company where we deal with some research projects. But you will see a bit more in the other presentations. Thank you all for coming, and good to see we have such a mixed international group. Great.
Okay, excellent. So how about Madhu? And Madhu is our distinguished professor in USC. He's also the director of wonderful program there. He actually on both sides, the aerospace and also the architecture. It's just amazing, and his knowledge and effort and skill is just amazing. And we have been doing several space tourism, right? Space architecture, space philosophy event, all led by Madhu. Madhu is great help for AIAA. It's wonderful. We are counting on your long-term support, and we'll support you as well. So Madhu, do you want to say a few words about yourself?
Oh, well,
or maybe
can I? Oh, good.
We still need to introduce.
Okay. Oh, there are lots of people for introduction, but first of all, thank you all for coming. And I want to let you know that this show is being run by Sandra and Alma. And I also want you to know, in architecture or in any other pursuit, posters matter. And for the first time, I will be asking privately of Ken, but I think we have managed to gather a good audience. Look at the numbers and you'll see we're approaching 100 people on online, Ken. It's a little less than 1,000, but that's how it works. But I want to welcome you all. And space architecture is a special arena, and I'm glad that your response is so good. And now I would like Alma to say something before we start the program. Alma.
Hi, hello everyone. I hope you can hear me. My name is Alma Kugic. I come from Pula, Croatia, and I'm a student of architecture at University of Technology in Vienna. I'm currently writing my master's thesis, and I'm also one of the co-organizers of this event. And I just want to say that it was a pleasure organizing it, and I am really happy to see you all in such big numbers. Thank you.
Thank you. Are we ready for the first set of slides, Ken? I can tell you that our schedule is already blown, but that's okay. But I think we are on schedule for, do we have a lineup, Ken?
Actually,
Not really, we don't need that.
Yeah, we have a group of people for session one. I
Okay.
don't know about, if you want to follow the
Good.
order. we can
In general, the way is that each of you have 10-minute slide or talk time, followed by 5 minutes of questions. And some of them may appear in the chat, right, Ken?
Yes.
The questions, good. And once that is done, we move on to session 2 and session 3. So enjoy the day with us here in London. I think our first speaker is Melody.
Okay. So it's Melody, right? Okay.
Melody, are you on?
Yes, I'm here.
Oh, great. Melody keeps a very busy schedule, flying around all over the place, and works for the pioneering company called Icon. I think all of you may have heard about them. And they're doing some spectacular work in North America, not just here, but in Mexico and other places. And Sandra is leading the effort as part of the architecture group for Icon.
I'm so sorry, Madhu. I have to interrupt you right at the beginning because I have to do the short introduction to the committee first.
Of course, yes, please.
I know that probably, I'm not sure if Mark is already here. Mark would have much more to say about it because we had some discussions, but let me start can you see my slides?
Yes.
Yes.
Okay,
Yes.
so I give a first introduction to the Space Architecture Committee, and then I will introduce Melody Yashar as the first speaker. So AIA's vision is to be the voice of the aerospace profession, and they have a tagline, it's shaping the future of aerospace. All right, so this is what we do. The Space Architecture Technical Committee is, one moment. Which slide do you see? I'm now a bit, sorry. Okay, the Space Architecture Technical Committee is the first formal organization of space architects and industrial designers in the world. It is one of 70 technical committees of the American Institute of Aeronautics and Astronautics, the AIAA, and each technical committee consists of experts in their field. Space architecture is the theory and practice of designing and building inhabited environments in outer space. This is a mission statement for space architecture that was developed at the World Space Congress in Houston 21 years ago in 2002 by members of the technical aerospace architecture. The founding charter further defines space architecture more broadly to encompass architectural design of living and working environments in space-related facilities, habitats, and vehicles. And also these environments include space vehicles, stations, habitats, and lunar and planetary bases. But it also includes Earth analogs and closed ecological systems. So this definition is from the Millennium Charter that was drafted by 46 architects, engineers, industrial designers, managers, and researchers in 2002. The entire text of the Millennium Charter is online and you can download it via our website. So it took quite a while. You can see on the left some video shots from this 2002 Space Architecture Symposium. And I give you now a short summary. Mark Cohen, probably later, he can give a more detailed description. Also Brent Griffin in the audience can, and Scott Howe. Those were the driving forces, and they are with us today. And for sure, they can tell you much more about it. At the beginning, the Aerospace Architecture Subcommittee was a subcommittee of the Design Engineering Technical Committee, DETC. And there was a group, Mark Cohen, Constance Adams, Brent Griffin, Scott Howe, Brent Sherwood, that had been looking for venues to hold first official technical paper session under auspices of the AIAA. So the first technical paper session took place in Orlando in 1999. And then later, Mark names it the first serious technical paper session took place at the ICES, the International Conference on Environmental Systems in Toulouse, France. And there was a lot of communication with many people in between and many phone calls and many meetings until the proposal of the World Space Conference was prepared, which finally resulted in the first space architecture session, as well as the first Space Architecture Symposium during the World Space Congress in 2002 in Houston. Here are another few snapshots from this epic event. It was kind of the start of our committee, but still not yet, there was no Space Architecture Committee. So in 2007, a proposal for an independent committee was prepared by Scott Howe, Ted Hall, and Brent Sherwood, Constance Adams, and Mark Cohen. And there were also discussions, interestingly, concerning about the name of the new committee. You can see in the text that it's highlighted, no other name can adequately express it. So the goal was to transform the Aerospace Architecture Subcommittee of the Design Engineering Technical Committee to the level of an independent committee. At that moment, there were about 30 members. They prepared a presentation and a document to address the concerns regarding the clarity and focus of the name. And on the left, you see a diagram that was also part of this proposal and that clarifies the relation between the SATC to two other AA technical committees, the System Engineering Technical Committee and the Life Science and System Technical Committee. Finally, the SATC was established as a committee in 2008. Overall, it was a 10-year effort, and now we are a professional association of space architects. We are very active and we maintain global research. At the moment, the Space Architecture Committee is structured like this. We have a chair and a vice chair. The secretary was implemented and merged with the role of the chair and vice chairs. They are elected for a 2-year period. We have 50 members that are from all over the world, from the US, from Europe, from Asia and Middle East, as well as South Africa. Our members are very multiple. They come from industry, academia, and government. And we also include experts as well as young professionals and students. We, SATC members, organize space architecture sessions at major technical conferences. This year it is the Ascent in Las Vegas, is the ICES in Calgary, and it's the AIAA in Baku, where we have multiple space architecture sessions. We also have honors and awards. So we also have Space Architecture Symposium in remembrance of our first symposium, where we meet for 1 or 2 days with new interested people to discuss applications of architectural principles to the design of facilities beyond Earth and living and working environments in space, and also technical challenges presented by the environment. We have Best Paper Awards in 2 categories every year. So we have a Best Paper Award for the Best Professional Paper and also the award for Best Student Paper. Relatively new, we have initiated the Gordon Woodcock Award, The Gordon Woodcock Award shall be the highest professional achievement of an individual in the field of space architecture. We are very glad that Scott Howe is here today with us because he received the first Gordon Woodcock Award in 2020. The award is created in honor of Gordon Woodcock. He was a Boeing engineering manager who had a pioneering understanding of the value of architects in aerospace. I'm also happy that Mark Cohen is with us today because he is the new recipient of the 2022 award of the Gordon Woodcock Award for Professional Excellence in Space Architecture. To use the tagline of AIAA, the STTC is shaping the future of aerospace. All our members are constantly progressing the field of space architecture. Many of our past and present members actively shape the future of space exploration right now. You will hear some of these as examples today, and on the images you can also only see some examples. That because they work at NASA and national space agencies from other countries and also in current space companies. Also, besides bringing relevant people in space industry, our members actively reach out and communicate their research in lectures, for TED Talks, and also publications and books. We have a huge open access database that you may want to note down. It's a huge resource of knowledge that is accessible via the web to everyone. And last but not least, we continue to encourage young people and to share knowledge. So many of our members are offering and teaching and accredited programs and courses. This is just a selection of the programs that are offered this year. So you can come to our website to see what's going on. And we invite you to get in contact with us. And those that are here and are interested in becoming a member of our STTC, please email me or follow us on our Instagram and Facebook account. We are very happy to welcome you and talk with you further. Thank you very much.
Thank you so much, Sandra.
I think there is no question yet. Maybe we keep the questions for our joint discussion after session 1. It is my pleasure to introduce Melody Yashar as the first speaker. Melody Yashar is a space architect, technologist, and researcher. She is the VP of Building Design and Performance at ICON. The projects are on the media, I think, in every country, in every newspaper at the moment. And I'm looking forward to hear much more about your work and what you do at ICON. Welcome, Melody. Okay, you are unmuted at the moment. We can see your presentation.
Can you hear me now?
Perfect.
Okay, wonderful. Sorry about that. I'm having some issues with my screen, unfortunately, but I'm going to just get started and hopefully be as timely as I can be. I have quite a few slides, but initially, well, first of all, thank you, Sandra, for the introduction, and thank you, Ken, for organizing this wonderful and epic event, and Madhu as well. Initially, I was going to speak about some work that we're doing relative to lunar construction, but this week in particular, the NASA Crew Health and Performance Exploration Analog had a press launch and also a press day where multiple members of the press and of media were invited to come into the analog. So I thought this would be a great opportunity to take a look inside what this analog actually is and talk about how it was designed and constructed. And I'll end with a little bit of how do we say it, a before and after kind of comparison of what we anticipated the interiors to look like versus what they actually are, which is not intended to be disparaging at all. It's just, it's the humbling reality that construction is rather difficult when you're organizing a research program of this sort. So CHAPEA is a research analog that has been designed and built at the Johnson Space Center in Hangar 220, which is actually where the Hera analog is. And it's intended to be used and operational for 3 missions, and they will each be 1 year long and house 4 volunteer crew members who will be simulating Mars activities within this structure. It is a 3D printed structure. Essentially ICON and multiple other former competitors of the NASA Centennial Challenge for a 3D printed habitat were provided an RFP to demonstrate capabilities to 3D print an analog habitat. ICON was awarded, and I actually joined ICON very shortly after that. So the design phase for this project began in October 2020. That took about, I would say, 6 to 8 months to design, and then construction began in June 2021. And I believe ingress for the research experiment is imminent. It should be happening sometime in the next few months this year. Some of the goals for the analog itself, the intent here, oh, did I lose full screen? Sorry about that. Okay, so sorry. Some of the goals for the analog, the intent is to evaluate on future long duration missions what will be an acceptable food resource or food supply for the crew members. Additionally, some research will be happening in crew health, behavioral performance, and just generally evaluating the behavioral performance of the crew. And the intent overall is to use that data to, in the future, establish and inform some standards and recommendations relative to future long duration missions. Grace Douglas is the principal investigator for CHAPEA, and she develops advanced food systems, both for space station as well as multiple other programs. So here's a rendering of the habitat printed by ICON's Vulcan system. This is our terrestrial construction system, which uses a mortar-based cementitious material, which in this case we dyed red to be more Mars-like, but the red is only a kind of a superficial sort of addition that we made to the material. This is actually the same material that we use to deliver all kinds of projects for sale in the housing sector, but also for the Department of Defense and all of the other sectors that we work in. So the system that was used to print this habitat is we refer to as the Vulcan. This is a gantry-based 3D printer that operates on rails. There is a maximum build volume associated with this printer, but fortunately for us, the build volume worked quite well with the requirements that NASA had for a single-story habitat in this case. We also, just to speak a bit about ICON's capabilities, we have a digital design to print workflow, which enables us to take BIM models, typically designed in Revit, and convert those models and translate them into functional and dynamic G-code that can be updated in real time over the course of a 3D print. And then finally, we have a front-end construction operating system that our operators use when printing, and it lets them know when certain interventions need to be made within the print, such as when reinforcement needs to be incorporated, or windows and doors and other fenestration and other elements. Finally, we have a workflow that we've developed to specifically introduce documentation for our printed wall. And this is something that is essential for us as we're permitting our structures and working with various jurisdictions to build our work in the real world. So here is the footprint of the CHAPIA analog within building 220, which is a conditioned space. And then over to the left, you'll see the HERA analog, the Human Exploration Research analog. The other thing to note is that both mission control as well as engineering support for both analogs are going to be within this building. That's for good reason, right? So that was the first of many constraints which indicated the maximum build size or square footage of the analog itself. The other constraint we had is that we were given a floor load rating of 500 pounds per square foot, meaning the overall structure could not be heavier than 750,000 pounds, which seems like a lot, but when you're working in concrete, that weight adds up very quickly. And there were a number of design iterations that we went through to be sure that we could meet that limit. So we were given quite a few requirements for designing the analog. In particular, utility connections were asked to be on the west side. We were asked to provide 2 exits, washer dryer, various other utilities, cameras covering the entire habitat, and of course that it was a single-story building. NASA was interested in this in particular because for safety reasons. And then we were given a minimum 1,500 square feet of living space to design for. The crew quarters, essentially we were told to provide a single bed, space for personal storage, and space for a chair and a desk. We were asked to provide a monitor within the recreation area, a table for activities, and comfortable seating. Within the kitchen area, we were given quite a few requirements. I won't go through everything just for the sake of time. And we were asked to provide 2 bathrooms, with 1 bathroom located quite close to an EVA area. The premise being that over the course of long EVAs, extravehicular activities, that the crew might need to go to the bathroom at some point. So they wanted to study how long they could go before needing to use the facilities. We were also asked to provide an exercise area within the analog, a medical station with a medical pass-through, which could include a 2-way fridge to pass biological samples to ground support. I mentioned bathrooms before, and then a robot R, basically flight simulator machine, which would be inside of a enclosed work, I would say, office space, where they would also be able to do teleconferences and video conferences for public relations purposes. And so some of the layout design principles relative to design of the analog, we were interested in separating the private from the public programs. Oh yes, we were working with the Bjarke Ingels group over the course of the design phase. And of course, we're working collaboratively with the Human Habitability Division, as well as multiple others from NASA, to refine the design and make sure that we were meeting all of the requirements in our design phase. But the idea of separating private from public spaces or shared spaces and creating a distinction between work and life programs were value systems that were very important to us. And we were also interested in providing some degree of multi-purpose or customizability within the design. So our process became, given that we had very limited a very limited footprint to work with, we established the general kind of, let's say, square footage requirements per program, and realized that we could create a sort of gradient in terms of the experience. Gradient meaning we are moving from left to right in terms of most private to most public areas. So that's essentially how the programming of the interior took place. On the far left of the screen, you'll see 4 crew quarters, as well as hygiene areas and some growth areas for crops, and aeroponic garden will be there. In the center area, we have a recreation area as well as dining area. And then on the far right, the work programs, the second toilet, fitness area, as well as the medical bay and robot R station. So here's the floor plan itself. And I'll run through some of the drawings that we developed for the habitat before speaking about construction. I'm going to try to go as quickly as I can. So you'll see the utilities on the west side of the facade, as well as the 2 access points on the east. You'll notice a very interesting panelized roof system. I'll talk about that in just a moment, but we were interested in creating in demonstrating an association between the roof panels, as well as some fillets and undulations on the facade itself, and also used it to separate those 3 spaces: the private sleeping areas, the leisure area, and the work areas. The roof sort of evoked a change in program and function. So here's some of the sections of the habitat. You'll see it creates this like that there's some areas where the ceiling height is lower than others. So in particular in the leisure room, you have a grander experience than you do within the crew quarters, which are more intimate. Here's a quick, what's it called? Time lapse of construction of the habitat. The thing that's interesting here is that printing of the vertical walls, not necessarily the roof panels, happened in about 10 days. And then finish out in construction of the analog took another, I would say, 9 to 10 months afterwards. So the printing introduces an overwhelming time benefit when we're constructing, when we're creating structures of this sort. You'll notice that the roof panels have pick points on them, and that's because they were lifted and lowered by an overhead crane at the Johnson Space Center. Here you'll see this is our typical 3-bead wall system. You will notice that the lines that are incorporated within the print are actually multiple types of reinforcement that we incorporate when we're printing our structures. Okay, so now for some construction images. We introduced a topping slab to redistribute the weight of the structure in building 220. We didn't do any, we were not destructive in any way and didn't touch the foundation of the hangar whatsoever. And you'll notice we also have 3D printed the formwork for the foundation as well, which in our opinion is one of the key strategies to reduce materials use in the future. Relative to, and presents an improvement to cast in place concrete construction methods. We printed the roof panels outside, such as you see here. And then once the vertical walls were complete, we lifted and lowered these roof panels using the overhead crane in building 220. So here you'll see the panels going on top of the habitat and the final result. All of our MEPs and general kind of, all of our MEP services were located underneath a raised access floor, which we provided, and it enabled us to make connections with the west facade of the structure. So you'll see these are the panels. And finally, our scope essentially finished here. Once we were done with electrical, done with the raised access floor, completed all of our utilities and our walkthrough for the habitat. And we had functionally no, let's say or involvement relative to outfitting and furnishing the habitat itself. We made many recommendations for how the two could work together to provide a more integrated result. But I think it was just an interesting experience to see how exactly the habitat requirements were reinterpreted for the sake of outfitting and furnishing. Okay, so I'll walk through some photographs of the actual habitat itself. This is an axonometric showing the habitat in addition to an airlock node located shortly outside of it, as well as a sandbox, which has been provided for the sake of doing EVA simulations on Mars. I'll mention really quickly, there's a paper that was presented in September at IAC where I discussed some of the regulatory implications of designing a habitat which does not necessarily need a certificate of occupancy from the city of Houston, but which was signed off by the fire marshal at Johnson Space Center, and what exactly that means for standards and and let's say requirements for habitat design in the future, but also for analogs too. It's an interesting thing, and I would love to dive into it at a later point. So, okay, this is a forgive the loud music in the background, but this is a fly through of the habitat, which was provided by NASA very briefly. And what I'd like to do is just show some photographs that were released this week in particular. So here you'll see the finished sandbox, which includes essentially an inflatable to show, convey like Mars-like surroundings. The idea is that the crew members, when they do EVAs, will likely be wearing VR and AR goggles to further simulate activities that they'll be doing. There's also some exercise equipment outside that should be simulating partial gravity. And they also are going to be doing some work creating regolith-based bricks, which is really interesting to me. This is a view of the airlock node, and then a poster that's inside of the analog for orientation's sake. Here's a picture of the food crop and growth areas. And I'll do a little bit of a before and after here, again, only to note how humbling it is when you have a grand design vision for interior space and programming, which may not necessarily align, let's say, with the overall intent and also scope and budget and timeline of multiple researchers and program directors who are hoping to satisfy the needs of this program. So in any event, here was our idea for the recreation area of the analog, and here's another idea. And then we ended up with this and some lazy boys, which I think is just a funny reality of working with this particular group. Here's another view of the working area. This was our vision for the medical bay. And here's a view of the interior. Here's our view of, or our vision for the working area, and then another vision of the working area. Granted, we did not have full requirements for every element that would be provided on the inside or exactly how the furnishings should go. And I mean, maybe it is a lot to expect that everybody would be paying for Herman Miller within analog research programs, but in any event, this was the final result. And the kitchen area, we actually did provide the millwork here. So we were able to introduce some degree of permanence for the kitchen area. And the crew quarters, this was our vision for the crew quarters. They're actually quite small, I should say. And this is the final result. And I believe I will skip this video for the sake of time, but thank you, everybody.
Thank you very much, Melody. It was a super interesting and very honored talk. Thank you also for this one. I think we can have 2 or 3 questions. Do you agree, Ken and Alma and Madhu? Because there was one question in the chat from Esther. Why not use additives to lighten the concrete? Or Esther, can you ask a question yourself?
Scott has a question, Sandra, when you're ready.
Okay, maybe she cannot ask it directly. The question is, why not use additives to lighten the concrete if the weight requirements made it difficult to design, which I think is a very smart question.
Yeah. How do I say it? I think that there are multiple approaches that we can take relative to material engineering for 3D printing. In particular, our system, rheologically, there's a tricky balance between establishing a flowable material that can basically get from our material handling system, the mixer, down the hose, and to the nozzle, while also maintaining enough viscosity so that you have structural strength and stability from one layer to the next. The thing about concrete in particular is that you're able to, well, first of all, there's lots of regulatory issues having to do with materials which may not have as much testing or data associated with them. In our case, this was not an opportunity for us to investigate an alternate material, so we ended up with our terrestrial cementitious solution that we have destructive testing for, as well as data, as well as general kind of structural guidelines that we could follow. So it was both a materials handling challenge, as well as one that that demanded that we revert to established structural principles relative to our material and structural design.
Thank you very much, Melody. We give the mic to the on-site location, Scott.
Yeah, hi, Melody. Awesome work. That's very exciting. One question that I had is, I recall the work that you did for the 3D printing competition that was earlier. And in that, you were attempting to do a kind of a pressure vessel with the 3D printing. Why did you and Icon choose to do a kind of a rectangular design here rather than try to simulate a pressure vessel?
I love that question. That's it, and it really gets to the heart of the matter relative to this project, which is that we were asked to provide or at least demonstrate capabilities to 3D print an analog habitat. And we were specifically asked not to address things like how we would introduce, how we would mitigate some of the risks of being in a true Martian environment. And so that was an interesting trade that we were asked to make. So we weren't asked to think about a pressurized interior. We weren't asked to think about radiation shielding as a design driver for the analog, because the fact of the matter is that building 220 is a conditioned space, and the overall, I would say, objective of the analog is largely to study human health and behavioral performance, not so much to introduce a design solution that could function in a Mars-like environment. And I know that's a missed opportunity, because like, it's only so often that we have a chance to create, I mean, this structure is like, costs a lot of money. There's only so often we have an opportunity to create projects that are this grand in scope and that are going to have such a applicable research program to future missions. But, you know, in the end of the day, everybody wanted us to maximize the footprint, not introduce rounded corners, because they're very difficult to program and outfit. And the constraints led to a fairly conventional rectangle, which felt like the most efficient solution given the constraints of the project.
Thank you, Melody. Sandra has clearly indicated that we should move along, and we could have more discussion later, right, Sandra?
Yeah, I think this is the only thing we can do, because we have already so many questions. I will copy them and we will answer them. Either anyone from us or Melody can answer them in the chat. And if not, we can keep them for the end of the session. Let's go to our next speaker, Brand Griffin. Thank you, Melody, for the great presentation, as always.
Thank you.
And now we have another wonderful talk, Rules of Thumb, Brand Griffin. Brand Griffin is the program manager of the single-person spacecraft for Genesis. But he is also one of the most smartest engineers in space architecture that I have got to know. In addition, he is a wonderful drawer, creator, illustrator, and I'm very much looking to what he has to say about rules of thumb, because he has experience with lots of past relevant space programs, starting from lunar outposts to deep space habitat. So very happy that you present your work or your ideas here today, Brent.
Thank you, Sandra. Can you hear me?
Can everybody?
Yes.
Okay. I don't know if this is working. Hello, Bill? Okay. Wow, great introduction, Sandra. And Melanie, you made it a very difficult act to follow there. So, and that's good news. I'm going to march through maybe something a little different, more words than pictures, but I think important information. It's called rule of thumb. Now, rule of thumb is a broadly accurate guide or principle based on experience or practice rather than theory. And granted, we don't have a long history, but we do have some practice. One example is measure twice and cut once. If you ever built anything, that's such an important rule to follow. Of these rules of thumb, some are obvious, most are biased, and the rest are controversial. They're intended to steer design engineers and space architects away from doomed concepts, while at the same time direct them towards areas that hold promise for being effective, workable solutions. And just a spoiler alert, some of these are darling concepts within the community of space architecture. I have a long list and then have compressed that for this presentation. You can see the ones listed there. I'll talk a little bit about inflatables, suit port, design for in situ repair and maintenance, zero-G shower, prepackaged foods, lava tubes, and circular floor plans. So with inflatables, I label this a solution looking for a problem. And the reason being is that we so quickly gravitate towards an inflatable, and that dominates the design space. We use the flexible membrane as the pressure shell. It's collapsed for launch and then expanded by the breathable atmosphere on orbit. It's a one-time deployment. Now, the argument basically stems from saying that our launch vehicle is so constrained, I've got to provide more volume on orbit or on the surface of a planet, and I'll do that by using an inflatable. The launch vehicles that we have now, from a 3-meter Cygnus to a 4.5 meter, the shuttle isn't flying right now, but a 5.4 meter from the Vulcan, a 7.2 from the New Glenn, and 8.4 for the SLS. Now, those are all habitable structures. And it's a matter, I think, of our design challenge to be able to do that. The typical solution for an inflatable is you'll have a rigid core and then you wrap that with a deployable membrane. So everything has to be basically wrapped around this rigid core, and at the ends of the rigid core are, berthing or docking ports in order to assemble the final configuration. It's designed to be packaged and deployed, which really adds a lot of complexity that cannot be underestimated. And that's from everything from your utilities to all your wiring and other things that have to be considered in terms of, I'm going to package them for launch and then expand them in the workable environments. NASA has a safety factor of 4 for habitable flexible membranes, and it's only 2 for aluminum. So the question of whether or not this is going to be lighter is a real one. It depends on basically the ultimate volume that you're going to have. But if you're going to use the argument of an inflatable being lighter, it may not be. The entire life of this habitat is dominated by a one-time deployment. And as I mentioned earlier, that there are many challenges in just doing that. NASA's inflatable transtab used a multi-layer polymer and Kevlar membrane, approximately 12 inches or 30 centimeters thick, that provided the NMOD protection. So that again is another aspect of providing important environmental protection for an inflatable. I mentioned the docking ports and hatches. You could include, and I think I've seen some images of radial ports that have been woven into the fabric structure, but most logically you'll have them, at the extremes of that package tube there. But a radial port is an important part of an architecture, and you don't want to just relegate it to saying, oh, I'm going to include notes. That having it there as being part of your overall pressure vessel is an important design solution. In my experience, length is a better unit for packaging than diameter. And that is because if you like single file packaging in order to have visual access and physical access, then you get that by length. You don't get that by girth. Windows, much like radial ports, can be woven in, but this is a little more challenging than including them into a rigid cell structure. And then the failure of a flexible membrane is catastrophic. We do everything to prevent that, but regardless, you lose your pressurized environment, you lose the pressure shell. So those are a lot of reasons for me not gravitating towards an inflatable, and in particular at the front end. If we're kind of forced into that, okay. Or, the option, and with a number of these things, if, let's say, your customer says, I want an inflatable, well then, as space architects, we want to give them the best solution. But this is if you have the choice up front, then these are some of the reasons why not to do that. The suit port. Basically, the suit port is a device to minimize the dust problem that we are going to experience on the Moon and Mars. And when you go EVA and being able to bring the suits back into any environment, it's going to bring that dust as well. So the idea is that you design the backpack so that it mates up to a structural interface, and then it ends up being the door through which the crew go in and out in order to get in and out of the suit. And the suits then would remain outside. And there are various concepts for that, whether on one side you see the suit lock and then the other is the suit port. The difference, the suit lock is you go into an airlock type structure, and then you can actually pressurize that volume. The other, with a suit port, the suit stays outside. So with this, the suit has to be designed for the pressure loads. In particular, if it's going to open up to the pressurized environment inside. We deal with a 4.3 psi in suit design for the most part. And then some of the different habitat concepts for the Moon and Mars actually have a reduced pressure down to an 8.2 psi. But typically, if you want the equivalent of Earth, you have a 14.7 psi. So once you open that door and you pressurize the suit, all of a sudden the suit is at the same pressure as the cabin pressure. So that's not a typical design that you have with a suit. And it also represents a very critical failure path. If anything were to happen to the suit, you'd lose that cabin pressure. So that's an important consideration in looking at a suit port or a suit lock design. Now, granted, dust is a real problem, and this is one means to try to deal with it. But in any event, at some point in the life of the suit, you're going to need to bring it into the pressurized environment for servicing. So you still need to do that. So you're still going to be bringing dust into the habitable environment. And because EVA uses the buddy system, you're going to need at least 2 suits. So that takes up quite a bit of real estate. And typically all you would need is a hatch to get through, rather than having 2 ports side by side for crew members to back up to. So these are some of the considerations for considering a soup port design in any of your architectures. We as architects ought to demand that our designs be serviceable by the crew in situ. So whether it's in a 1.6G environment, a weightless environment, and bring that requirement right up front and really make it work. It's not good enough to take 3 or 4 parts out before you can get to the one you want to service. And as the expression up above says, it's difficult to change the fan belt while the motor's running. And our equivalent is, let's say, with the environmental control life support system, can you turn that off and service it? Or, does something still need to be providing environmental control for the crew while they're servicing that? These are things that we have to consider in our design. So access, also how you remove them. And again, we're not sending career mechanics. We're sending astronauts that have another function, where they're going than servicing their equipment, but they're going to have to do it. So we've got to make life easy on them by us incorporating all of the features that are required to make the equipment serviceable. So, there are some components that are scheduled to be replaced, others that just fail all on their own. We have to deal with electrical, electronic, and fluid systems. Fasteners, especially like in the weightless environment, should be captive, so that I can back it off, move it out, and I don't have to be chasing some floating washer. The harnesses, they're a big deal. They're a big deal on the ground, but in space, they can represent a certain structure that's resisting us to be able to remove a component. And how we gang up components too. The whole idea of what an ORU is an important strategy, and it should affect us as designers. Then moving down a little bit, in the weightless environment, unless a crew member is in a foot restraint, they can only use one hand. They have to anchor themselves with the other hand, use that as a restraint, and that's not a very good working position. So being able to provide a foot restraint so you have both hands free is important. The lighting, any other things that we have, be sure to include those in our designs. Zero-G shower. Melody showed a shower, and that was on Mars, and that makes sense. There's a little gravity there. We have one experience of that, and that was on Skylab. And you can read up there where only Jerry Carr claimed to enjoy it. Fellow crew member Owen Garrett said he would skip the whole thing. Now, in the weightless environment, the water doesn't know which way to go. The air doesn't know which way to go. So we have to provide some way to move it. And with the Skylab shower, you can see it was a collapsible membrane. They spent quite a bit of time getting together. I'll read it. You had to mix water in a 3/4 container, so much hot, so much cold. You had soap that was probably better used for veterinary practice because it made you itch. We sprayed water on ourselves with a sprayer and then had to vacuum it off with a suction device. He goes on to say, one thing worth noting is that we were in a low pressure environment, and so whatever you got water on you, it went to dry itself off. It got extremely cold because it was evaporating so quickly. It took a lot of vacuuming to get all the water out of the inside of the cylinder. You had to use a lot of towels to get dry. During our mission, we usually just took sponge baths every night with a washcloth and a towel. So with all of that, you wonder, should I include a shower? Is it effective, and is the crew going to use it? Now, Skylab was, I believe, 5 psi pure oxygen environment. It was compatible with a lot of the Apollo life support systems. So we're dealing with 14.7 typically, but regardless, in the weightless environment, our sponge bath is good enough. You still need to exercise, so you're going to be working up the sweat that way and also from EVA. but to include a shower is a major ordeal. Prepackaged food favored over growing in situ. And Melody, I think you showed some plant growth areas in your solution there. The overhead. Hold on. Okay, I think we got that fixed. But the overhead associated with producing any food is tremendous, and also there's a risk. If you have a crop failure or something like that. Not all of our, food would we like to be growable. There's other things that we can bring along, and to consider that we have nutritionists looking at not only what food, but our whole caloric intake, what we need for nutrition and everything, and bring it with us seems to be a safer, more reasonable solution, at least for the near term. Their near term could be 20, 50, could be 100 years, but regardless, for the crew to be able to do that rather than presume that we're going to be pretty good farmers and spend quite a bit of time, producing and processing that food for the crew to eat and to have a healthy diet. Lava tubes, again, a darling subject. It's one of those ones where, hey, there's something out there. We can use that for a habitat, or at least maybe for radiation protection. Well, as a habitat, it doesn't make a lot of sense because we know nothing about that in terms of it holding pressure loads that we would need, and even its geometry. In terms of radiation protection, yeah, it could work, but we're going to have to put something in there. The other options would be that we bury it and just pile up a lot of regolith like on the moon, or there's some independent structure upon which we put the regolith. Again, we're using the regolith as the radiation protection on the moon. So lava tubes, again, looking at those, really, I would want to see that they might work, but I think it's a dream, and it's probably not going to come true over all the analysis that would be required in order for us to put our habitats in or try to somehow live in a lava tube. Circular floor plans. When looking at a lot of these, and over the career I have, that if you can avoid this, you're better off. The modularity with a radioconcentric plan is difficult. We tend to migrate towards more of a rectilinear solution and packaging and changing things in and out. In fact, if you look at this little diagram here, if you were to try to make a wedge-shaped modular, you couldn't remove it. It would be that you have to remove the content. So it affects the modularity in terms of packaging. It affects the distribution of utilities and being radial and concentric. Whereas if you have a linear one, it's a lot easier to pop up access to all of your utilities. It, again, ends up being rectilinear in terms of the modularity. And going back to one of the other metrics that I mentioned, that length versus girth tends to be favored for a lot of reasons. And in this, in order to make it work, you have to have some kind of increment that would deal with an aisleway in order for the crew, or just make big, larger spaces. Now, if I'm going to make a bathroom bigger and have the same components in it, it's no more efficient. So we want a right-sized bathroom. And I think you can get that easier with a linear solution versus a radioconcentric. That is the presentation. I wanted to compress it. I don't know how we did on time, but I'm open for a few questions here.
Sandra?
Thank you very much, Brent. We have a few questions. I think the first one was from Samuel. What about lessons learned from Bigelow Aerospace?
Say again? Is that the question?
Well, it was a comment or a question, but he asked about lessons learned from Bigelow Aerospace and TransHub.
Lessons from TransHub.
Lessons from TransHub? Oh, that was a pretty major study that was done at JSC, and you know, we have a number of our space architects that were involved with that. And you know, I think we learned a lot in how we could build, let's say, an inflatable solution. But I'm not talking about that. I'm talking about given the choice. You know, is that what we need to do? And are we overlooking other things that are available with some of our large diameter launchers that we have right now that could solve the problem of the habitat without going through the complexity of actually inflating it?
And we had quite a few comments. Are there questions from the audience?
Yes, good morning. Hello, hello, can you guys hear me? Yes, good morning, guys. Rick Garcia, background, current U.S. Space Force. Okay, is that better? Yes, so great presentation, sir. Can you go back about 5 charts where you had the airlock? Okay, so the suit lock and the suit port. So one of the things in my experience, professionally speaking, integration, capital I, is a massive consideration, right? When we're talking about space architecture systems, ecosystems, and system of systems, right? So are you guys considering integration into your footprint of the design? And what I mean by that, it's not just for, in a sense, today, but the downstream effects. So one of the things that we've encountered with the integration kind of system of systems approach is, if we design and we look at integration and try to consider a lot of front loading, that suit lock may have additional benefits for like an emergency type of situation, right? So just want to get a feel for when you guys are working on these type of systems, do you guys consider in your technical footprint that we might have to consider additional side benefits to just the initial task at hand? If that makes sense. Over.
Yeah, it does, and I think that's an excellent question, and I'm a firm believer in the integration of system to system. I think as space architects, that's what we have to do. Now, the option to this is having a traditional airlock. Okay, you get in, there's no suit interface, you know, and then you would doff your suit, and then you go into the other environment. So ideally, the cleanliness would happen in that space. The only thing I'm trying to point out here is that by having a suit port or a suit lock, you're throwing requirements onto the spacesuit to have a pressure interface there. And if you do that, now, the one that I mentioned, I think is the biggest one, is that the suit has to now take a load that it wasn't designed for. If this is designed for 4.3, that's a lot. You know, now the suit's going to become a lot heavier, a lot more, you know, I guess complex, because it has to take anywhere from an 8.2 to a 14.7 pressure load. Okay. And you break that, yeah. So that's a consideration here. We're not, you know, we are going to go EVA or we're going to go out in suits, but it's whether this is the solution or whether a more traditional airlock that you would get in, you close the hatch, and you open the other hatch.
Right, right. And I guess the follow on or the other question within that sub question is, if we're building the systems of systems now, and I'm biased towards automotive because I've had experience with like Formula One, Aston Martin racing. Now I need to open my mindset about multiple vendors, right? Because it's just not going to be NASA. It may be SpaceX. It may be a tertiary, a subcontractor space that may design a suit, right? A different manufacturer. So if that thought process of universality or universal fit is embedded in there, I'm biased to think that if you build the suit lock system, maybe it's easier for you to do a universal fit approach, right? Because you can have downstream benefits 5-10 years down the line where you have on-ramping new vendors, right? Rather than just form fit function for one type of system, right? Does that make sense?
Yes,
Over.
yes, it does.
Because we have more speakers, so Ricky, you can more questions later on.
Okay, Sandra, is Alma next?
Yes, I think it's me next, right? Or is it Alma?
You decide. I'm okay with both.
Yes, Alma, you're next.
Yeah, Alma is next.
Oh, okay.
Then I have the pleasure of introducing Alma. Alma is an architecture student at the TU Wien, and I'm very happy that she chose the TU Wien to do her diploma in space architecture. She is living and working in Pula in Croatia, and she has also joined, or she's an active member of the Adriatic Aerospace Association. So I think her goal is to become the first Croatian space architect. And since this year, she has been elected as a member of the Space Architecture Technical Committee. I know Alma for a few years now, and she has been on almost every space architecture competition that I know, and taking parts in workshops all over the place. So today she's presenting her diploma project, and it would be great if you give great feedback to her. Good.
And Sandra,
Yes.
I want to mention that Alma had a huge hand in our beautiful poster. And,
Yes.
I'm looking at the crowd here. All the seats are taken, Sandra. And I would thank Alma for it.
She's a great, well, in the SATC, I have to say, she is busy with many things. So she is a very active member. And besides other activities, she is also co-chairing this event. Yes, thank you, Alma.
Thank you very much. Thank you. Thank you so much. Let me start. Well, today I will be presenting you my master's thesis topic. It's called Explore, and it is Lunar Exploration and Habitation Rover. The thesis is still not finished. It's still in process, let's say. So some design issues can be changed or can be upgraded. So, but this is like the so far, how does it look like? So let us start. Just a second. All right. Well, the Explore is a lunar exploration and habitation rover. It is designed as a proposal for the Artemis Space Camp. And if we talk about NASA's Artemis program, it aims to land astronauts on Moon by 2025, and also to give those astronauts a place to live and work on the Moon. NASA's Artemis Base Camp concept aims also to develop a modern lunar habitat, a lunar terrain vehicle or LTV, and also a mobile home, or it's often referred to as habitable mobility platform. And this habitable mobility platform should be optimized for extreme lunar environment, should also be used for in situ scientific exploration and human and cargo transport, should also be suited for 2+2 astronauts, which means that should host 2 astronauts and another 2 in case of emergencies. It should have 2 weeks long effective autonomy and be adapted to dimensions of the transportation vehicle, and also to be able to be configured differently according to function. And to this part we will come to later on. I would also like to mention the Artemis timeline. As you can see, we are quite busy in this decade. Lots is happening. Basically, Artemis 1 has been done last year. Next is Artemis 2, that is happening next year in November 2024. And Artemis 3 and 4 This is when the humans are going back to the surface of the moon. And so the year 2025 is quite important for the Explore because it has to be finished soon. So it could be taken to the moon along with these humans, or actually before them would be perfect. Moving on to the location, to the Artemis location, it's the lunar South Pole. It is a good target for a future human landing because it is the most thoroughly investigated region on Moon. And the landing site on the South Pole has not yet been determined, but all of these sites of interest that you can see on this image have many advantages compared to the other locations on the Moon. For example, all of them have available sunlight. They also have permanently shadowed regions with potential presence of water, mild temperature differences, relatively flat terrain, and most importantly, Earth visibility and direct communication. If we talk about requirements and rationale for the Explore, I will not go into this entire list because we don't have much time, but I would like to mention a few of them. Of course, the requirements for the crew capacity, you already mentioned 2 + 2 astronauts, because the safety and performance is prioritized. I also thought about the mission duration, 2 weeks for short-term missions, also to minimize the commute back to the base at the end of each day. But the Artemis program is searching for at least 10 years of mission duration, let's say, for the longer periods. Then I also should mention that, of course, lunar environment survivability should survive extreme temperatures of the lunar South Pole and operate at least 2 hours in a permanently shadowed regions, should be, of course, resilient and adaptable. Robotic manipulation, of course, to support science exploration because it offers greater diversity in scientific research from geology to water ice sampling, and should be able to be operable by onboard and remote crew on lunar surface or Earth. And I think this is everything I'll mention from this list. Moving on, I did also a comparison list. Just a second. The comparison list, I have compared Lunar Cruiser, the lunar terrain vehicle, and Athlete, also in order to understand vehicle concepts better and also to adapt certain parameters to the Explore and also maybe to improve them. But also I will not go into this list in detail because we don't have much time. I will just skip on to the vehicle habitation concept and vehicle logic. As you can see, lots of sketches have been made in order to find let's say a perfect form, and it does not mean that the perfect form has been found, but the vehicle logic, let's say it consists out of modules or pieces, other pieces, for example, the cockpit, the rocker bogie chassis, also the payload that goes onto this chassis. In this case, it is the habitation module and the robotic arm. So if you take a look at this first icon, you can see the Explore, the side view in this compact form when everything is put together, but it can be detached. For example, the cockpit can be detached from the chassis and the payload can be also detached from it. So, and if you look at it in the top view, I call it, you can see that it's also compact. I call this a mobile configuration because this is the configuration that is used when the Explorer is traveling on the lunar surface. We have packed inflatables on the side, and the cockpit is of course connected to the chassis and to the payload, to the habitation in this case. But when it's standing still or when it's time to maybe stop traveling and do some scientific research or rest or sleep, then there is a stationary configuration where this packed inflatable is inflated. It's depacked and inflated. And the idea also behind this, as you can see, this top view, this mobile configuration, it is important to think about what do astronauts need, what do they have to have always available, like the dining, the kitchen, the living area, and the hygiene. But in stationary configuration, it is, sorry, just a second. Can you, sorry. Okay. In stationary configuration, when the shell is inflated, you get also the science lab, the gym, the crew quarters, and the sleeping pods. And here you can see it better. How does it look like, this modular design? We have, of course, the detachable cockpit. You can see it better here. The detachable cockpit has suit ports. Actually, it has suit locks. It also and can be also used as separate vehicle. We also have this expandable habitat. It actually, the chassis can carry any kind of payload, but in this case we have this expandable habitat, also with airlock and 2 suit locks on the back side. You cannot see it now. We have the rocker bogie chassis that is used as this habitat's wheels and can also be used for cargo transport. And we also have robotic arm that is used for sample collecting for scientific research, and also as a spare wheel when the cockpit is detached. So if we talk about transformable architecture, we have this. I have already mentioned the mobile configuration earlier. Then we have the stationary configuration when the inflatables are inflated. We have the cargo transport. This is only the chassis connected to the cockpit without the payload. And then we have the separated configuration. As you can see here, the cockpit is using his robotic arm as wheels. And is also used for going faster if it's necessary to detach from the habitat and go somewhere faster and going back faster. Right, the floor plans. Even though there is only one floor, or there is 2 floor plans, because when the shell is deflated and when the shell is inflated. Here you can see how the cockpit is connected to the habitation. In between is an airlock and, of course, the tunnel, which can be disconnected. Here you can see the suit locks, and you exit through here. Later on, there will be an image showing how this happens. And just mentioning pretty quick, the kitchen, the dining, and the living, as you can see it on the other image as well. But when the shell is inflated, the science lab becomes bigger, becomes usable. You can see the container that the robotic arm is putting samples in, and also the crew quarters are usable at the moment. The main entrance, or the part where you connect this vehicle to the main habitat or the main base, happens at the end, at the rear end. There is a hatch door with standardized measures, but there is also suit locks on the back, which I also have an image later, but this part can be maybe changed. Moving on to the section, this is maybe to get a better view of how big everything is, and how big humans are in this vehicle. Of course, the top part is used for habitation and living and working, and the bottom part of the vehicle is used for engine and batteries and life support systems. Right, so also here you can see a section when it's deflated shell and when the shell is inflated. Right. And coming here to the last slide, this is a perspective section. It's quite important, I think, for people to see how does it look like in 3D. Maybe for some of you will be easier to imagine themselves in there and to get a better perspective of how everything looks like. And here on the side, actually just a little explanation of how the suit locks work. Actually, we have here a side panel on the cockpit that slides 1 meter, and then the suit port, actually the suit is visible. So astronauts can exit and enter through here. So there is 2 suit locks on the cockpit and also 2 on the habitation. Here you can see this is the main suit port entrance and exit, where the back panel or the lid rotates for 150 degrees. And if the docking is happening when the vehicle is connecting to another habitat, the back panel or the lid rotates also 150 degrees, but together with the suit ports. All right, so this is everything from me for now. If you have some questions, please ask, or if you want to send an email also to ask something or to have some talks, arguments, you are very welcome to do that. Thank you very much.
You are next, Sandra, but I had only one comment to make. Whenever I see a little rover like this, I'm reminded of a project that was done at Boeing by none other than Brand Griffin, called the Daylight Rover. And have you seen that, Alma?
Yes, I have. Yes.
Oh, you're popular. Great. Please go ahead and ask any other questions, but I think Sandra knows how to keep time better.
It would be great if one of you has a question to Alma. If not, I asked the question that is in the chat from James. Instead of a modular rover, what about using multiple rovers for mission effectiveness?
Yes, good question. It is actually in plan to use at least 2 rovers for the first, actually for the third Artemis phase. It is supposed to be only one rover, but for the next Artemis mission, it would be good to have 2 of them on the lunar surface. They are meant to work together, so to say, and be connected with each other. The overall mass, that is a big question. Since the material has not yet been decided upon, the overall mass has not yet been calculated. So, yes.
That's the most difficult questions to our students.
Yes.
What's the mass? Okay, there was one question by 2 questions, but we keep the questions until the end. One question, the launch of the rover, would it fit in the current launch vehicles?
Yes, even though it would not fit, it would have to be detached. It would not fit when it's all attached to it, all the modules attached to each other, but detached would fit into Starship.
Okay, thank you very much. Unfortunately, we have agreed to 2 questions per presentation. So we will keep the questions until the end of the first session and then go through them again.
Thank you very much.
Thank you, Anna.
May I introduce you, Sandra?
That would be lovely.
Okay, now Sandra has been working at the Vienna University of Technology for some years, and she has a most excellent group of students every year. I'm jealous. And she produces not just manuscripts and conference proceedings, but books upon books of works that her students continue to do every year. And I see her at conferences. Most recently, she took a bunch of her students to the UAE and presented at the expo. Am I right, Sandra? Do you had something to do there? And,
Yes.
and you know, it's delightful to see Sandra handle a very large number of students. And I was so happy to talk to a class. I'm sure some of you will too. I know that Marco and Ash, have you, Brad? Oh, we got a willing victim here, Sandra, and Scott too is smiling over there. You know, welcome you, Sandra, and we look forward to your presentation.
Thank you very much, Muthu.
Of course, please tell us about you before you present as well. You know, I'm just excited to see you.
I have a short presentation because we have a few others coming up, but I show you some recent projects. So we just started an exhibition at the Technical Museum in Vienna that is showcasing our research on space architecture. It's quite a special exhibition because it's an arrangement with the TU Wien, and it's called the Science Corner. So I think we're the first architecture department that is exhibiting in the Science Corner of the TU Wien, and we show some projects there. I show you some of the exhibits right now. This is the Haven Lunar Port by Sabrina Kerber. Sabrina Kerber is now, of course, a space architect and has finished. She works in Holland. This is a design for a landing and housing facility on the moon's south pole. And for her, the sustainable reuse of discarded lander components to create this launch and landing area for incoming and outgoing crews was important. Her design is a long-term habitat. The habitat is equipped to...
Sandra, sorry, we cannot see the presentation. You're not sharing the presentation. Okay, sorry.
Okay, no, I thank you very much. Otherwise, it's a bit boring. Good. So this was the first image of the exhibition at the Technical Museum. Then, can you see it now? Okay, this is the project from Sabrina Kerber. It's a lunar port and base. So it's a habitat for a permanent crew and a non-permanent crew, and her focus was on reusing discarded lander components. So the habitat is equipped to accommodate a permanent crew of 4 who will work at the arrival port and conduct research on lunar habitability. And in addition, they will have accommodation for 4 astronauts for 7-day acclimatization and training before they will be sent off to other research outposts. So this is like the lunar port where the crew arrives and it departs. The architectural concept is designed to address the challenges of a multi-crew approach, which has potentially social issues among to be solved. The habitat itself comprises of a rigid central core and a multi-layer inflatable. And in addition, the habitat's radiation shielding is made of empty propulsion tanks from discarded lander descent stages. So the radiation and micrometeorite shielding makes use of in-situ resource regolith in conjunction with this discarded propulsion tanks. So the benefits are immediate safe disposal of the excavated material during the pneumatic process and great time efficiency, because many processes can run simultaneously. And furthermore, the approach prevents the need to launch additional machinery to create the regolith shielding to the moon. The regolith field tanks are placed around the habitat and serve as the horizontal shielding, and additional regolith field bags cover the habitat top. The habitat itself is spread over 2 levels, a surface and a subsurface level. On the surface level is the entrance to the habitat with 2 airlocks, and there's also a greenhouse module and a green gallery, and they have also included a cupola window to watch the stars and to interact with the plants on the green wall. This is the 3D printed model of one of my projects. Here, the challenge of uncertainty was part of the lunar-based design, because there is the moonwalk is based on the premise that space and its elements are closely related to human behavior. And the challenge is in planning space for unknown user with changing requirements. So the considerations include a few levels of adaptability. For example, to ensure long-term functioning, it is required to change the research site, mission objectives, and other mission-related details. That is why this lunar base is mobile, and it has 6 legs that function as landing, standing, and locomotion tools, and occasionally as bionic arms. Then the inflatable rigidized structure offers 12 docking possibilities for plug-ins and expansion to adapt to future mission scenarios. The structure is multi-layered that permits partial exchange in order to enhance radiation shielding and protection from meteorites. And the interior of the habitat can also be adapted according to changing user preferences. This is a model that is designed for a deployable habitat for long stay duration missions on Mars. It is a system that is compact for transportation and can be expanded when placed on the Martian surface. For this, the team developed a deployable structure that consists of 4 subsystems: a protective casing, a telescopic core, expanding girders, and an inflatable membrane. The habitat will be transported in a compacted form and placed at a selected location. And of course, we assume that there are numerous previous robotic missions to Mars that have prepared the necessary infrastructure. And once placed at the right location, the 3 casing elements unlock and the deployment sequence is initiated. And then the compressive springs of the girders are released, pushing the casing elements radially outwards. To ensure radiation protection and MMOD shielding, the design uses ground-up regolith to fill the outer layer of the membrane in the final deployed state. The habitat ensures a protective environment for a 4-person crew, and is offering radiation and micrometeorite shielding. Natural light is provided by cupola, and the core acts as a circulation distributor horizontally and vertically. The central space will be naturally lit during the day, and all the modulars can be expanded by placing multiple modules of them. The next project is a project from Ivan Matas. This had the aim to conceive an orbital facility for the recycling of space debris. For him, this was a big issue because debris of any size poses an imminent risk to all current and future space missions. And worldwide concepts and technologies are being developed to find solutions how to remove debris from orbit. The vast majority is based on capturing and deorbiting the debris, casing it to burn, and during atmospheric re-entry. So his idea was to use the material where it is, in situ resource utilization in orbit, and as it may present a valuable resource for future on-orbit construction. So the main focus for this work is towards the architecture and the design of an orbital space station that is made to research on how to do on in situ research utilization in orbit with space debris. The resulting space station, he called it at R3 debris, which means research concerning resource utilization and recycling of debris, is capable of housing a 4-person crew of 6 to 12 missions and up to 8 people. It contains a shredder for rough processing, a robotic arm, and a thrust platform, in addition to a habitat module. And the module concept is similar to NASA's Trans Hub and the Bigelow Aerospace BA330. Its interior layout features private quarters, also a social hub, hygiene and sports facilities, and a greenhouse. And everything is planned to be arranged in a non-conflicting way within a very limited volume. That is another view of the exhibition. So if you're in Vienna, come by and visit the exhibition and me at the TU Wien. There are a few more models to see, and also some engineering and scientific aspects to consider. And before I introduce our next speaker, I would like to draw your attention to our brand new MBA. We have a Master of Business Administration in Space Architecture at the TU Wien. It started this year, but it is a circular program. It is a 3-semester part-time program, blocked in modules, and spans an arc between economics, engineering, architecture, and other technical and social sciences. So in case you're interested in this MBA, please contact me or visit their website. And I thank you very much for listening to me. And I see if I have questions before I introduce the next speaker.
Any questions in the chat, Kim?
Okay, Esther, yes, please come and visit let me know when you come and we can go and visit the exhibition together.
Did you say that the exhibition is on in Torino?
No, in Vienna for 1 year now.
Okay.
It's a 1-year-long exhibition.
Okay.
All right, I think there are no questions.
I have one, Sandra, and how many students do you handle every semester?
Well, I have different kinds of students. I have the master and bachelor students every year, 50 to 60 in the module. This is why I invite you for a lecture, for example. Then I have some special design studios. One is being introduced by Paolo Caratelli in the next presentation. We had the pleasure of working together with the Abu Dhabi University and worked together in a design studio. Here we had also 40, 50 students. And then we have the MBA program. This is less. We only have 15. And I have another program that is for adolescents that are 14 to 16-year-old. Here I have 20 students for 2 years. So quite a few.
Space architecture is popular brand.
Yes, well, yes, it is becoming more and more popular. I get more and more questions for diploma. More and more people want to do the diploma or dissertation. We need also more lecturers to handle that.
We're always available, Sandra. And you know, I think it's very interesting to know that even in Southern California, I mean, we are sitting right next to SpaceX here, we have a lot of interest in thinking about new visions about space. Now, please continue with our next speaker, Sandra.
Thank you very much, Madhu. I have the pleasure of introducing Paolo Caratelli, who is a very nice colleague and became a friend. In the last years, we worked together. Paolo Caratelli is associate professor at the College of Engineering at the Department of Architecture and Design of Abu Dhabi University for over 10 years. He's also a licensed architect in Italy and a researcher on architectural and urban sustainability, and investigate about social and cultural changes in architectural design. He has also started a program on extreme environment architecture at his faculty at the Abu Dhabi University. And yes, Paolo, good to see you.
Nice to see you too.
Please, the floor is yours.
Thank you, Sandra, for the introduction, and hello, everyone. I'm start sharing my presentation. Okay, that is Sandra has been part, as she introduced, is a collaboration that we initiated, and a collaboration that born at the Space Architecture Technical Committee, where we were colleagues, and we start discussing and trying to find a way how to have a shared educational collaboration. So we, in the fall, during the fall semester 2021, we started this idea to have a cross-national design studio between the design studio of TU Vienna and 3 sections of sustainable design course at Abu Dhabi University. The first challenge was the pandemic, obviously, because we were still in pandemic, we were partially still in lockdown. So it was not only the problem of communication between Vienna and Abu Dhabi, so from Europe and the Middle East, that can be solved doing the course essentially fully online, but it was also the problem how to deal with our students, because we had limited opportunities to meet directly. Despite that, and despite the other challenge that it was how to harmonize the 2 different levels, because the 3 sections of Abu Dhabi University, for a total of around 50 students, they were undergraduate, and the 10, 12 students of Vienna, they were postgraduate. So how to harmonize the 2 for this shared project that we named Lunar Oasis, like an homage to Middle East. I mean, the idea of the oasis as the place of life in a hostile and extreme environment. We solved practically creating mixed groups of projects, around 10 groups. And these mixed groups, they were designed as really design teams in terms of professional. So with a group leader, usually obviously the student with bigger experience, and 5 to 6 members that they will collaborate with the research and design and all the efforts towards the production of the final outcome. The outcomes, they have been beyond our expectation. All the groups, they work really, really committed, and all the works they produced something that despite, especially talking about Abu Dhabi University students, it was the very first time that they face a similar task, a similar challenge. And they have been driven even into the general problem of sustainability. So we tried and we gave all the information to let them understand that sustainability in space, like in every extreme environment, is not an option, is a necessity. So you have to do everything with less. Waste is a resource. The concept of waste not even exists. So despite the initial alignment and the try to better understand how to realize a project in an environment that doesn't allow you so much, and going beyond the usual and traditional mindset that okay, I have to build something, I can use reinforced concrete, I can bring metal, I can bring panels, so we invited also them to have this project, first of all, designing the mission, and so giving all the requirements and the limitation that a similar project could have. So starting with Oasis as a concept, and this is following, it's only a brief collection of some images per each project, just, I mean, to give you a glimpse, but all the projects at the end, they were done within 1 semester. So 1 semester, I mean, 4 months, working in groups that they were necessarily contacting themselves only online. A total of 60 students at the end, belonging to 24 different nationalities with different even time zones, so even to accord each other related to the timing. So at the end, it was an extraordinary experience, not only under the pedagogical aspect, but even in terms of cultural exchange, relation, and the final result that you can see here, that have, I repeat, are only, I mean, 1 or 2 images for each project, but each one was really supported with extensive research and an extremely deep and thought work. And considering all these challenges, all the problems related how to connect each other and how to coordinate, I think that has been a fantastic personal, professional, educational, a fantastic experience. I don't know how many of these 60 students they would become in future space architect. Surely someone, yes, for sure, and there are. Surely some students, they already asked me, and the same here in the spring semester, in the following semester, I had two students at Abu Dhabi University that they asked to have a graduation project about this topic. Many other students are continuously asking, especially in this region, since that UAE became one of the country member of the Space Club. There is an Emirati astronaut now on orbit, and so even the interest and the expectation also in this region of the world are constantly growing towards this kind of field of specialization. Most of the project they used largely class 1 and 2 habitats, so from rigid to inflatable, some even challenging, some groups also challenging with class 3 habitats on the moon surface, which means using in situ resource utilization largely. And this is practically the detail of one of the last projects. This one has been the only one opportunity that I had to meet with my students in person after already several months. We were in October and we start the course online end of August. So after more than 1 month that we spent online, this was the only one opportunity that we had to meet in occasion of the AIAA in Dubai. And we have also the opportunity to meet Hazza Mansouri, the very first Emirati astronaut on that occasion. We had an interesting conversation with Dr. Peter Weiss of Spartan Space about his project EuroHub. And we had also the pleasure to meet Olga during the AIAA at the exhibition. So thank you. Not only after, in January 2022, we had the opportunity to present the outcomes of the entire course at Expo. This is the poster that we prepared announcing the official presentation of the course, the outcomes, the projects at the ASEAN Pavilion. And also in this case was an extraordinary experience. Unfortunately, not all the students, we were still with some issues for international transportation, but we had the opportunity, me and Sandra, finally to meet in this occasion. And we had the presentation at the ASEAN Pavilion and the final one at the Swiss Pavilion. After that, the course, Lunar Oasis, has been presented at the General Assembly of UNOSA in Vienna, and has been presented also at the AIAA in Paris. This is a shot of the interactive presentation that was presented there. Last but not least, we produced, a consistent, thick booklet, are around 200 pages of with all the synthesis of all the projects. And here you can see, only some pages even to evaluate and to understand the quality and the efforts that this heterogeneous group of 60 students, they produced in only 4 months, and for mostly of them really starting from scratch, not having before had any clue or any information of what an environmental control life system will be, or a bioregenerative life support system, or how to integrate a greenhouse into an enclosed environment without talking about other issues like radiation protection, micrometeoroids, and so on. So, educationally speaking, and as a teacher, I have to say that this has been one of the most interesting experience, and something that we, both myself and Sandra, we are working, to repeat. Now I'm also pushing more in my university and in the College of Engineering to include this as a subject, a potential subject, and including a larger and more vast topic related to the architecture in extreme environment. Thank you so much. I think that I remained within my 10 minutes slot. And if you have any question, please, or later on during the panel discussion, I will be very, very pleased to respond to all of you. Thank you so much.
Thank you very much, Paolo. We have one question. Is this published somewhere from Esther? Well, yes. Yes and no. We have a public ISO account, but it was restricted a few weeks ago. So it will be online very soon in the next 2 days. If any of you would like to get this booklet in a printed version, please write to Paolo or me.
Please.
Okay, any other question?
Paolo, this is Madhu.
Hello, hi Madhu.
I was happy to see you at the IAC. And again, my question is, are there any other programs in that part of the world dealing with space architecture?
Unfortunately, not yet, not specifically, addressed to space architecture. In fact, the very first experiment, and one of the challenges was exactly this. It was to introduce within the general course of sustainable design. And so starting with this and asking the students to look, sustainable design means that you have to use as much you can regarding the sustainability. And one of the best place to test everything in terms of sustainability, spatial arrangement and technologies, process methodologies, why not to use as paradigm space as the most extreme of the extreme environments. So based on that, even my department start to have a look, and in fact, we start building another course that will be dedicated to architecture in extreme environments, which is include obviously desert, Antarctica, underwater, but specifically to space architecture, not yet. And I hope something would start soon.
Excellent. Any other questions for Paolo? Please come over.
Hi, Ben Price. Curious, I love the UAE. I've been there before in Abu Dhabi, it's a beautiful place. Have the Arabs brought any unique insights as desert dwellers, as cross-Saharan travelers to that concept of no waste and very efficient use of their space and their resources? They brought any unique insights that you found?
So, I mean, UAE currently is doing lots of efforts in order, I mean, especially in terms of resources. As you know, in this region, in this part of the world, is more easier to drill a hole in the ground and find oil instead of water. Water is, I mean, what the very precious resource that here. So most recently, UAE has started a massive campaign of sensibilization, and also in terms of how to save resources, save energy, and also the courses, obviously university courses, they had this input to specialize and to assess more and more courses and specialization in terms of sustainable environmental sustainability or advanced technologies. I would like to add just, I mean, has a small addition related to the importance of sustainability in our field, which is also a very powerful driver towards innovation. So space architecture is not only I mean, exotic or something a fancy way to do architecture in a different way. Is really architecture for another environment, is really something that would drive and would push the new generation to even to better understand and to reframe what they are thinking about the current ordinary architecture on Earth. So we are constantly talking about spin-in, spin-offs, and one of the most important spin-off from space architecture is exactly this, the capability to see our ordinary architecture with new eyes, maybe, or at least I hope.
Thank you.
Thank you so much, Paul. Any other thoughts? Or Sandra, shall we go to panel?
Yes, I think our next speaker is Mark.
That's right. Okay.
Mark, are you here?
Yes, I'm here.
Wonderful.
Yes, I've been keeping quiet.
I know. Sandra, will you introduce it?
Yes, but only so far, right? Mark Cohen. Mark Cohen is, I mentioned him already in my introduction about the SCTC, because he is one of the masterminds of that this community committee, technical committee exists. Mark Cohen is a licensed architect. He has devoted his career to developing the new field of space architecture. That is also one of the reasons why he was awarded the Gordon Woodcock Award, which is the highest award in the space architecture field. Mark Cohen worked at NASA Ames Research Center for 26 years, then at Northrop Grumman, for 4.5 years. He had his own companies, and I know Mark as an enthusiastic space architect who is, I don't know if he likes this description, but I consider him as walking library. He knows everything. He writes really wonderful papers. So if you haven't read papers from Mark, go to our website and have a look at his papers. Okay, thank you, Mark, for joining us again today for the Space Architecture Technical Committee gathering. And we're looking forward to your presentation.
Okay, let me try to get it up here.
And before I hand over the talk to Mark, is it working? Oh, good. I would like to say that Mark is very much a no-nonsense debater, and I've enjoyed his wisdom over the years, including from the time I was graduating in school, when my professor knew him, and he asked me, "Have you read Mark Cohen's papers?" And that's when I picked up. And my thesis had Mark on the reference, and he questioned me, he quizzed me and said, "That is not the right way to use me." But since then, we've been very close, and welcome you, Mark. And of course, he's also a grandpa now.
Yeah,
and
I'm
Mark,
just trying to, can you hear me?
we can hear you well, but
Yeah, I'm just trying to figure out how to get this screen set up properly to share the screen.
You are on screen now. All you need to do is go down to the bottom, and click on the screen icon. That's it. It should do it in
Keeps wanting me to sign in again.
Try to click the screen one more time, the screen icon. And no, I meant on the bottom.
On the bottom where it says notes, comments, and then you have some icons. It says 105%. There is a note. Go down with the mouse down.
All right, okay. It says you are screen sharing.
Yes, you are screen sharing.
You see my screen?
Yes.
You can see your screen. You know, if it's difficult.
Okay, I just can't get it.
Full screen.
Or go to slideshow on the top where it says home insert design. Go to slideshow.
Slideshow.
No? Yes, slideshow.
I don't see where.
Okay.
Well, I can't get. Oh, wait a second. View. Okay, slideshow. Ah.
Okay.
All right. So,
Mark, before I let you have your say, are you the only person in our group who really knew Buckminster Fuller?
I don't know if I'm the only person.
I think Brad did
there were two earlier people. Zan Gill, whose paper I presented at the 2002 First Space Architecture Symposium, she worked for Buckminster Fuller, and also before her, I had an intern whose name was Sharon Skolnick, who had worked for Buckminster Fuller. But I may be the only one on this Zoom call who knew Buckminster Fuller.
Okay, please go ahead.
Okay, so the title of this paper is Innovation and Tradition in Space Architecture, and I actually wrote this paper as an invited keynote address for the PHI Congress that was supposed to be held in Lisbon, Portugal, in 2021, or actually 2020, but it was canceled 2 times. anyway, I published this paper, or they published it in their proceeding, and so this is actually the first time I'm presenting it to anybody. You can see the paper was the URL to get it from our online bibliography is here on spacearchitect.org. I don't know if you can see my pointer, but that's where to find the complete text of the paper, which is a lot more extensive than what I'll say in this presentation.
Yes, we can see it, and
Okay.
I know you send it to us.
Good. So, as a general approach, in most societies today, people balance their lives between tradition and modernity. Everybody is sort of doing a balancing act between the two in various ways. And modernity often relates closely to innovation, or at least a positive view of innovation. Similarly, tradition and innovation engage in a dialectical process in which the new transforms the old, but also the old informs and influences the new in certain interesting ways, which I'll touch on in a few cases. So this essay presents a view of these dynamics from my perspective through my career. Now, in writing this invited paper, I was told it should be a personal account and should go into my own experiences. So I do that to some extent. So this is not sort of an impartial, objective, analytical study. So Buckminster Fuller was my earliest mentor. I became interested in him when I was in high school, and I followed a lot of his projects and developments, attended many of his lectures, talked to him whenever I had the opportunity. And he talks about his Dymaxion principle, which I think is probably the best distillation of his work as a philosophy. And so in one of his books, Ideas and Integrities, Fuller recounts a conversation with Dr. Jonas Salk, who was the first inventor of the polio vaccine. Dr. Salk said, "I've always felt that these Dymaxion gadgets, cars, houses, maps, etc., were only incidental to what you were really interested in. Can you tell me what your work is?" And Fuller answers, "Yes, I've been thinking about the definition for a long time. I've engaged in what I call comprehensive anticipatory design science." And Dr. Salk said, "That's very interesting because that's a description of my work too." So from this, there are three elements, which is, first of all, comprehensiveness, seeing the big picture, the integrated system with all it entails. And this is important because, in fact, there are an awful lot of people who don't see the big picture, either because they're unable or because they're unwilling to see the big picture. Then anticipation, foreseeing what the building, the house, the invention, the operation, the system will need in its future developments. And I think that's a really key aspect, which is to foresee what will be needed from as empirical and objective a point of view as you can, rather than what you as a designer would like it to have. And then design as science. This is the idea that not only should there be a rational empirical basis for design decisions, but that it should derive from a testable, empirical, and I should say falsifiable basis, which is the way it's really discussed in scientific theory, in the scientific method. Now, another mentor I had was Robert Maycall, who was the founder of System Engineering, who served on the Space Station Concept Development Group at the same time as me in Washington, D.C. And he had several consulting contracts to come to NASA Ames, where I got to know him quite well, and we talked a lot. And I believe that Maycall surpassed Fuller in the comprehensiveness dimension of the Dymaxion principle. So Maycall and Good's seminal book, System Engineering from 1956, presents innovative, systematic, and quantitative approaches to analyze and solve complex design problems. And fortunately, we had a first edition of that, which I read. It's really a fantastic book. It's hard to find, but it's well worth it. It was subsequently published in another version as a System Engineering Handbook, which has been published and republished in many forms, and NASA has adapted a so-called System Engineering Handbook, which tends to be very formulaic and prescriptive. But from Robert Maycall, I learned to ask always, what are they not seeing? What are they not considering? What are they not taking into account? And what he would always say, what happens if you calculate that? So Maycall's vision differs from the current system engineering religion, as I think of it. Because in his view, it was an open-ended approach where you're trying to get the comprehensive picture, consider all the variables. But in the current system engineering religion, everything must be reducible to a deterministic number or it is not important. And so I think the direction that the system engineering discipline has gone has really veered off from what Robert Maycall originally intended. So this leads, whoops, went the wrong way. This leads me to something I think of as systemic blind spots in each of the disciplines of architecture, engineering, and science. Architects look at the big picture, but their grand concept as a design solution tends towards the egotistical and overlooks key practical aspects in the design of a space habitat in a lot of cases. Engineers tend to wish to believe that everything is reducible to a quantitative problem which there must be somehow a quantitative optimization or a deterministic solution. And I discussed this to some extent in the paper. And scientists want the best possible accommodation for their experiment or their instrument or payload, but they tend to be reluctant to see or embrace the larger design problem and solution of incorporating that instrument into a larger space probe or satellite, or incorporating it into some other vehicle or planetary base or whatever. So each of these disciplines has their blind spot. And I think of this in something that's called, in terms of something that's called the symmetry of ignorance, that everybody knows some things well, but everybody also has areas that they are not well informed. And whether or not they recognize that is important. So now another source, sort of philosophical source that I have is Maimonides, who was a philosopher and medical doctor in the 12th century. In his Guide for the Perplexed, he presented a model that postulates a concept of truth and falsehood as separate and disconnected from the concept of good and evil. And I think this is important. And this is a little diagram I concocted that kind of shows my interpretation, which is that these are two completely separate axes that really only meet at the 0, 0 coordinate. Tradition, I believe, tends to adhere to the horizontal axis of good to evil, which is really a matter of gray values, where you're asking, is A a little bit better than B? Can I make a little more money with C rather than D? What'll have the best return on investment? And this axis of thinking on the gray scale of good and evil, I see as a trap in terms of innovative design. And what I want to do when I'm trying to design is seek what Maimonides called the necessary truth. And I think of this as the innovation scale, the vertical axis between truth and false assumptions. So I'm going to talk about the suit port, which we heard a little bit from Brand earlier. In terms of the necessary truth that went into the design concept for that, or the design inspiration. So I designed the suit port in alliance with the AX5 spacesuit project. That was the Ames Experimental 5 suit. It's an all hard suit, operates at 8.5 PSI. So it's about double the 4.2 PSI of the Apollo era and shuttle era spacesuits. And this photo shows the AX5 mounted on its rear entry donning fixture. And the astronaut subject, Phil Culbertson Jr., is evoking the Da Vinci's Vitruvian Man with his arms and legs. And the AX5, of course, was designed by Vic Vicukal at Ames. It was the fifth in the series of AX spacesuits. And it's made from machined high-strength aluminum forgings. All of the pieces are, and it has a very high safety factor, except for the gloves. The gloves are the main weak point in the suit, in any suit. So here's the suit port, mated to the rear entry port of the AX5. Now, the original purposes of the suit port were these four. First of all, save atmosphere, and the revelation, the necessary truth, is that was no need to pump down an airlock volume. The airlocks, the conventional airlocks, or big dumb airlocks as we used to call them, were anywhere from 6 to 10 cubic meters of air. That puts it in the range of 200 to 300 cubic feet. And the assumption was that we would pump that down to save the atmosphere and conserve it and reuse it. But the revelation of for the suit port was that if we seal the suit rear entry to the pressure bulkhead, then all you need to sacrifice is the small interstitial volume between the suit portable life support system backpack and the inner hatch. So what we're doing is we're saving atmosphere, saving crew time, minimizing the need to pre-breathe pure oxygen, because the AX5 is 8.5 PSI suit, and save a considerable amount of power necessary to pump down, which I calculated at 5 kilowatt hours. So anyway, you'll notice that preventing contamination or controlling contamination was not one of the original purposes. That didn't come up until later, when we had a funded project for the so-called hazmat vehicle. Now, here is the longitudinal section through the suit port, and it's actually in what we called an EVA access module. The idea being that the whole EVA system needs its own access module. You can't see it here, but there is a hatch between the cabin and the airlock volume. And so the suit is is in an airlock volume which nominally is kept depressurized, but can be pressurized for the crew to go in, inspect, or repair the suit. And the funny thing is that somebody somewhere in the EVA ecosystem came up with the idea of a suit lock, and the suit lock is basically the whole of the original patent. And then people started referring to the suit port as just the suit mounted to the bulkhead without an exterior protection. But anyway, you can see the way the astronaut would enter and don the suit and reverse the process to doff it. Now, to protect the glove against failure, the patent includes what we call a glove back pressure device, which protects it against blowout through the fingers to hold the cabin pressure. And here it is, the way Mike Gernhardt, the astronaut exploration EVA lead, put it in the Lunar Electric Rover. And this participated in the Desert Rats. It was also the NASA float in President Obama's first inauguration parade in 2009. So now I'm going to talk some about tradition. There's been a tremendous amount of theoretical writing in traditional architecture, which I read, and I don't hear them as just kind of speaking only to art historians, or which is where most people ever learn about it. I experienced these theorists as speaking directly to me across the centuries and across the millennia. But in contrast, most architecture students receive a very deficient education. They get a very watered down Vitruvius. They basically learn just two mantras. Firmitas, commoditas, and venusitas is one, and the other is the mantra that the column is the principal ornament of architecture. But there's so much more, and I'll give you one example. Vitruvius proposed the first definition of privacy. And he wrote, the private rooms are those in which nobody has the right to enter without an invitation, such as bedrooms, dining rooms, bathrooms, and all others used for the like purposes. The common are those, meaning the common rooms, are those which any of the people have a perfect right to enter, even without an invitation. That is entrance courts, cavadia, peristyles, and all intended for the like purpose. The cavadia is the same as an atrium. It's the large central room in a Roman house with an opening to the sky, the impluvium that rainwater can come in and collect in the pond underneath, called the impluvium. And here's an example of the first private sleep compartments in space. They're from Skylab, where there are 3 sleep compartments for each of the 3 Skylab crew, and they're all different shapes to give them some individuality. And here's the Skylab 2 logo with a Vitruvian man. So now, I'll give an example from Palladio. In his 4 books on architecture, he offers 3 formula to calculate the ceiling height of a room based upon its proportions and size of the floor area. So I applied Palladio's methods, his formula, when I was needed to calculate the height of the ceiling for the Space Station Proximity Operations Simulator, which really basically meant how high from the top of a fiberglass cylinder we were going to place the floor. And I did that, and it seemed to work out quite well. Now, I'm going to talk about the cupola on the space station. In the upper left, you see the Duomo in Firenze, the big cathedral dome in Florence. And there are things that attracted my attention were, first of all, the radial rondel windows around the base of the dome, of Brunelleschi's dome, but also the cupola on top. And I had the idea that for what we then called Space Station Freedom, before it became called the International Space Station, that we could attach a skylight, or rather a cupola port, a cupola onto a radial docking port, or any other docking port. And we managed to get that into the space station configuration. Here you see a cupola in what was called the RUR2 configuration from 1985. And then here you see the actual cupola attached to a module on the space station. So here the necessary truth was where you put a cupola, considering the fact that these modules had very limited possibilities for attaching a completely new penetration. And so the idea was to convert a docking port into a mount for the cupola. So I actually have a conclusion. It's kind of wordy and convoluted, I'm afraid. This basically presents my understanding of innovation and tradition and how they interact in space architecture. And unless one knows and comprehends the design precedents and the traditions they embody in the history, you cannot anticipate or comprehend what constitutes a true innovation, or if such an innovation is needed. And then space architecture is all about living and working and surviving in space. It's the study and theory and practice of design for space living, etc. These environments support crews, bases, settlements, towns, and cities in orbital microgravity and in partial gravity. Now, new space architects tend to assume that because they are entering a new field, that whatever they do must, as if by default, be new or innovative. But this is kind of a fallacy. And it doesn't have anything to do necessarily with knowing what is the necessary truth. Because I don't think it's possible to approach a design problem with the assumption that I've got to do something completely new. Because that biases you from understanding what the real requirements are. So unless you know thoroughly the precedents and the tradition, and we are developing our own traditions within space architecture now, to which Brand spoke, however much I disagree with some of the things he said, one cannot know what innovation is or what it needs to become. So, the end.
Whoa. Thank you, Mark. Say something? Or do we go to questions?
Question.
Yeah, Mark, when you talk about tradition, for some reason or the other, I'm thinking Fiddler on the Roof. But that's beside the point. And I agree with a lot of things you say. And, I remember Arthur Raymond, the DC-3 designer, came to school, and he said something that's obvious but not very well understood among professionals. That is, common sense is not so common, and this happens to us as we enter more and more specialized areas of work, and it's particularly true for how we treat people in in spacecraft. And so I kind of agree that you cannot quantify everything and put them down as numbers. Many things defy quantification. They're qualitative, to be precise, and that is why we have the law, and that is why doctors treat us. Everything is not quantitative. But anyhow, I'm opening up to questions and then a panel, because we are only running an hour late, Ken? Okay, questions for Mark.
Oh, that was not a question?
Oh, well, do you have an answer?
I don't have an answer. No, I couldn't detect the question.
Okay, good.
We have one question by Alma. Alma, do you want to ask the question yourself?
Is it Alma?
Sure.
Okay.
Yes, hi. Hi. I wanted to ask, how does the astronaut exit the suit through the suit port? Can he do it alone, or does he need help?
He can do it himself. We've different groups have built full-scale prototypes, and in every case, the astronaut can get in and out by herself or himself. That includes NASA, JSC, University of North Dakota, and the Ames hazmat vehicle, which I guess I should have showed a picture of that.
I've seen images of astronauts entering the suit, yes, but I've never seen an image or a video of exiting. So I don't know, how does it exactly look like?
Oh,
like
well,
from the back.
Well, I guess they're all still stuck in their suits. It looks, getting into the suit looks a lot like getting out of it if it's a photograph. Okay. I'd have to think of where I could find a video of that. But yeah, I'm sure that there's something out there that shows it.
Okay, thank you.
You're welcome.
I have a question to Mark. The Palladio and Vitruve books, you read them in English? Or
well, actually, I've read them in English, but also the best version of Vitruvius is actually one in French that was published in, I think, 1680, which is all cross-referenced. It's actually the best translation of Vitruvius for those who aren't fluent in Latin. But yeah, there is translations of all those into English.
I think Sandra mentioned Palladio, not.
Yeah, Palladio, Vitruvius, Turlio, etc. Alberti.
We have another question by Steve Sturck. Mark, everyone, do you have any parametric cost model by KG, I don't know what this means, that you recommend for the space architecture lunar community? Like, what is the cost for the suit?
For the AX5, well, the AX5 would have cost about $1 million a copy in like $1987. That doesn't include the portable life support system.
Mark, we still need to write a paper on that, about the evolution and the politics involved in the creation and the disappearance of the AX series, right?
Well, you start writing it.
That's how it always starts. Any other questions, or shall we move to the panel, the incredible panel? Is that the plan?
Wait, Madhu, we have one more speaker before the panel.
Sorry.
That's Maria, but please, can I have one more question? Because
Sure.
Mark surprised me today with his privacy comment. Because what you said, what Vitruvius said about privacy is almost the same definition that is provided for privacy from scientists in psychology. You know that privacy, where intruders are not, or the private space is that space where people are not allowed to enter. This is almost the exact definition of environmental psychology.
Right. Well, I don't know if I can take credit for that, but you know, back before most of the people online were born, I was promoting the Vitruvius definition to environmental psychologists, and including Jim Weiss and Yvonne Clearwater and some others, and they liked that definition, and so I think maybe that's where they adapted it from. I think I first published it in like 1984 with the seminar on space station human productivity at Ames, and you know.
Okay, that's super interesting. I think I read it. Gifford was this environmental psychologist, but maybe that means it's the truth, right? When you have definition for so long.
And Sandra, am I right to think that privacy and the envelope is very different for different cultures and different peoples around the world? How do we fit that envelope into an astronaut category?
But I think that's the point what Mark just explained. His definition is universal. It's not cultural dependent, because he explains the definition where intruders may not come without an invitation. He doesn't say how large, you know, nothing about dimensions, nothing about time.
Interesting.
It's just that it's a very universal definition. That's interesting.
Yeah.
Of course, the design for such a privacy looks different.
Yeah. Okay, who's next, Sandra?
Next is Maria.
Oh, Maria.
Marino, we invited her to talk before our panel.
Okay, now may I introduce Maria?
Please.
Oh,
please, Madam.
And now, long ago, I'm not going to say exactly when. I know Brand is laughing over there. And we were all at the inaugural session of a program at MIT. And Maria was kind of the head honcho there. I don't know how she wrangled it, but everybody, when they had a problem, would want to go to Maria. I really don't know if she knew anything, but it was all directed at Maria. And then I realized that she was a nuclear engineer at the time, and she went on to head up several divisions at Alenia, and she promotes space and space activity like very few people I know. And somehow Maria avoided the agencies and went into the industry, from where she is going to provide us some words of wisdom. I hope, Maria, it's so nice to see you. It's very late in Toledo, and you have Mars background, but so glad you're here. Please tell us what you think, and maybe a few words about yourself first.
Yeah. What can I add to what you just said? I I am, more than pleased to be among so many longtime friends, including you, Barbara, Brand, Sandra, Olga, many of you guys.
Oh, did we lose your contact, or are you still there?
Yeah, it's frozen. Maybe we wait a bit.
Anyhow, when she comes on, we could do the panel, I hope. But she has wonderful insights, looking from the industry viewpoint that we'd love to have her speak to. While she is still figuring out, any other questions before we move to panel? Oh, good. Okay, who is joining us? Scott and Brand? If we need to be formal, I think we are.
Hello, Madhu, I'm back.
Okay, wonderful.
Sorry.
Okay, Maria,
Sorry.
Please go ahead.
I don't want to take too much time because we are well beyond the time allocated to the first session. Just wanted to maybe share with you the industry point of view. I've been working in Thales Alenia Space for 37 years now, and I don't just said I saw, I participated to the development of, how can I call it, the first really inhabited large infrastructure that we are lucky to have in orbit around our planet. And I love to hear the way Mark recall the importance, for example, of cupola. We in Torino, we are the designer and the producer, the manufacturer of cupola. So I have a presentation, but I don't manage to share it with you guys, but it doesn't matter. The point that I wanted to make with you is the following. Every single word that was spoken tonight is important. The totally open-mindedness that comes from the students that have a completely unbiased view. I adore listening to Alma. I adore listening to the presentation by Sandra and Paolo, reporting about so many different student projects. But I also thought that was proper for Brand and Mark to point out that one thing is to imagine, one thing is to be creative, to develop new concepts. Another thing is to put them into reality. As Melody properly said at the beginning, when she explained, how can I say, when she showed, in fact, the different results, the initial architectural layout and the final, not rendering, the final real, how can I say, outcomes. And the same is true for industry. The good news that I want to share with all of you is that we take into account all the philosophical, let me call it, philosophical and cultural approach that Mark just pointed out before. So we position the human needs in the center of every design activity that we carry on. Sandra, in fact, came to Torino when she was finishing up with her university degree. Sandra came for her thesis to see how the modules were in fact designed and realized in practice. And so man is our, man with man, human, men and women needs are at the core of our design activities, but then we have to cope with the constraints that come from the launchers, that come from the money available, and so on. Well, we are currently welding the new modules for the lunar infrastructure that will orbit the moon in a few years from now. We are welding, not designing, welding the modules that will be part of the new commercial infrastructure around our planets. We are designing the lander and even a pressurized rover, ALMA, not so similar to the one that you show. That would be like a Ferrari. We are currently designing, how can I say, a Fiat 500. You're not Italian, but it's just to, how can I say, compare the dream with the reality. But we are moving in the real world, and we do our best to contribute with the infrastructures that in the near term will be part of our, how can I say, travel toward the moon and Mars. And I thank you for allowing me to share with you an industrial viewpoint. If you have any questions, I'm happy to let you know, for example, that as much as I would like to have huge volumes available, to accommodate beautiful internal architectural layout. For example, for the gateway, we have to stay with cylindrical modules, 3 meters diameters. So there are constraints that, for the time being, limit a little bit what we can do, but still the technology is making enormous progresses. We can use virtual system for sure. 3D printing, as Melody said before, is not just good for terrestrial analogs, but is also good in space. And so technology is helping us a lot.
Sandra, I think if you want everybody to take picture, you need like Barbara and Sam, everybody to turn on the screen. And
yes, wonderful.
Okay, let's go over there, and Brad.
But you look great on the panel over there. Please stay there. Brand, Scott, Madhu, it looks great if you stay there.
That's like better here.
Okay, so you remain the seat and you take a screenshot.
All the others, okay. I cannot take a screenshot from all. Can you do that?
I think we want to be all together with
That's
the
right.
Yeah.
Good idea. Let's move Barbara. That's right. Person and
Sam, if you're here, please turn on your camera.
And Claire too.
All of you.
All of you. Let's see.
Okay, let's write. Please turn on your camera.
Let me 1 second. I think what happened is they only allow certain people on the spotlight. So let me try to do this pin using the pin instead.
You can use my camera too, Ken.
I understand, but it's not it's a background.
Okay.
Because they seem to be limiting people, how many people can be.
But do we see all participants? I think I only see the.
That's the issue. That's the issue.
Will it help you go there?
No, it's not.
Well, Bernard's approach usually asks everybody who is in, come to the screen, and he takes picture of the screen with people standing in front.
Okay, so be patient because we have 2 screens here. So we will just have some people on one screen and one on the other. So we have is already there. So let's remove this. Then we have Ontario is not there, so we add him in. So who else? Alma is there. Sam doesn't turn on his camera. Sam, where are you?
Oh, I see what you're doing. Yeah.
We had a nice
Put in
shot
certain number of
with
pure-
200 tiles from Paulo. We'll put that one on.
Yeah, okay, so I think we have, we are missing Sam.
Okay.
Not Samir, is Sam. Sam is,
Talking to me, I'm here. I think the camera is on, right?
okay, 1 second. You're.
Not Samir, Sam Jimenez.
Oh.
We have
Yeah, Sam Jimenez.
two Sams.
It's Jimenez. He hasn't turned on his camera yet.
Yeah, probably he is not available.
All right, so we just ignore him now. Take a picture. Forward, right? Yeah, they are forward.
And where is Brent and Scott?
Guys,
Don't forget her.
if we need more, we'll have it will be $5 per shot.
No, she's a speaker, right?
No, we need a picture. Where's Brent and Scott? Where is our panel?
Sandra,
Yeah,
we're not online.
Brent left an hour ago, I believe.
She's
No,
not-
I saw him just a few minutes ago.
Okay.
We're not online, we're here in
Yeah,
reality.
in person.
Yes, but where are you? You look so great on the panel. The panel is empty now.
I see what you were saying. She was
And Ken, here, yes, Ken, you also need to be on the picture.
I'm okay, I'm
You
okay.
have been such an important person. You have to be in front.
No worry, no worry.
That looks great. Next time we come to LA, okay?
That's right, we need you here.
Wonderful.
I've been
So
watching.
Ken, you need to go.
Okay,
to-
after this.
Okay.
Okay, we're good. One more. Okay, take one more for me. I will go next.
Ken is going to come.
Yeah. And
Let's go
include.
right on that side, Ken. Right over here.
Okay, over there.
Wonderful.
Let me take one more back here. Let me take one right here.
Okay. Sorry, Jeremy.
Yeah, this one's better. All right. All right, I think we got it. We got
Great,
it.
thank you, Mike. Thank
Yeah.
you. Thank you.
And guess what? We are only halfway through the event. That's good that you took a picture of me.
Well, this is in case it's very late for some of them.
Oh, that's right. Yeah.
Yeah, so we agree, remember?
I know.
Yeah, take a group of it.
Thanks for reminding.
Yeah, because at the end, some.
Thanks for reminding, Sandra.
Thank you.
Thank you.
I don't know what it is. I don't even know.
Okay, guys, it's time for a panel
So the panel is for session 1.
for session 1.
So
Okay.
for the session 2 and 3, we'll temporarily turn off your camera.
Oh, all right, good. Okay, so go for it. I found, Sandra, it's your turn. I keep taking the mic, but it's your turn. Go for it.
1 second, for folks here, since this is lunchtime here, we don't have time for lunch break. So some folks might have gone out to grab their lunch. And once again, we have bottled water, coffee, tea in the kitchen. So we all do benefit from it. So in case you want to walk over just 30 seconds across the street, there's a corner burger. You have American food. So enjoy. Thank you. Go ahead. Sandra, go ahead.
Shall I go ahead?
Yes, please.
Okay. I think we have to limit the discussion a little bit. But what I find pressing as a theme now that it was not planned, but this relation between innovative designs and reality. Maybe we could have a discussion on how we can ensure that what we think as professionals, experts, based architects, designers think is relevant for habitation how can we make sure that it will be built that way? Because so far, I mean, with Brent, I wrote the paper so far, and also at Thales Alenia, you worked 15 years on this habitation module, at least, with I don't know how many man hours, and it was discarded, and all these things get discarded. But how can you make sure that we have a sustainable space development and important things are not discarded? And Melody, you know, she had this wonderful honors presentation. That is, I think, a very big issue that also Mark probably can sing a few songs about.
I don't know, Sandra, if you ask the question to me or to anybody. I can maybe start by answering that we are used to work a lot side by side with astronauts. So we collect first-hand feedbacks from, how can I say, the real experience in space of what we have designed and realized so far. And so, for example, we were talking about cupola before. We collected many years ago, I remember myself, a feedback from a cosmonaut, Polyakov, medical doctor, who told us that what he really missed was the possibility to, how can I say, have a look outside without feeling like being in a confined environment, a sort of can. And so the idea of cupola started to develop. Some other astronauts underlined the importance of the crew quarters, as one mentioned before. And as we all know, in any current design, crew quarters are a central part of the internal layout. But also the social zone is as much important as the private one. And so it's a balance. We need to look for proper compromises, how to best use the little volume that is available. And as I said before, technology is a big help because the possibility to use advanced materials, expendable materials, the possibility to reconfigure the volume to allow for, how can I say, a minimum creativity of the astronaut themselves is very important.
Yeah, let me add to what Maria was saying that early on, even before ISS, and Mark referred to some of that, working with Boeing, that was some of the things that I did. We built full-scale mock-ups, and then we brought on the crew at that time that had the longest space experience. Bill Pogue, Jerry Carr, they were our consultants. And we tend in many ways to think that all astronauts are equal. They're not. You know, and in fact, I think you need to be careful about what advice you get from what astronauts and how much time they've spent on space. Past that into the early development ISS, I was the habitation module manager, and we built that up, and we had full-scale mock-up, and in fact, built the pressure vessel, and it's in Huntsville right now. It hasn't flown. We have not flown a habitat since. What we've done is we've kind of squeezed crew into laboratories, and I don't think we've done a very good job there. So, as space architects, you know, addressing your question, Sandra, I think we really need to look at space habitability, and in terms of maybe a dedicated module that does that function, and we haven't had that.
Do you want to say something, sir? Okay, let me add to this. I think all of you all of you space architects, both practicing and aspiring, you may know that humans in the loop cause a lot of rethinking in design. And this goes back to our early capsules, and where the designers were hardcore engineers who did not want to have their thermal or life support being messed up by people. And one thing led to another, to the point that the astronauts told them very clearly they were test pilots in reality, and they needed to see where they were going because they did not want windows. And there are instances like that. I think we lost somebody. There are many instances like that, and so when crew are involved, I think qualitative aspects are tantamount to good design. Mark may have things to say.
Have a comment back here?
No, the comment is that's the concept of human-centered design. I think it's really important, well, critical for designing a habitat that humans will be in.
Question?
That's right. Human-centered design is another way to put it. Talk about it.
Appreciate the panelists, team members here. A lot of great insight. So one of the really amazing products that we are experiencing in Space Force, some of us as young professionals, is we really are looking now at the digitization of the service, digitizing the models, the systems, the platforms. And it's almost being done like at a kind of, we're being taken to school. And the best analysis that I can use, I had an opportunity to spend time with Aston Martin Racing at Formula One in Monaco. And one thing that was really amazing that I noticed that they digitized all the model of their systems before they even built any structure. They actually do it in a digital ecosystem, and they have teams that focus on thermal engineering, teams that focus on human factors on the race car driver, teams that focus on aerodynamics, teams that focus on communication. And what was really cool is that they could model these systems in a kind of simulated environment and test them before they even push them out on a laboratory. So I'm wondering, have you folks experienced any of that digitization, or are you seeing that as an emerging kind of philosophy with some practical application in your career, your spheres? Over.
Yeah, I can take that. I'll take that at first, but probably Melody might have something on her experience as well. I was involved in the HDU, which is the current Hera project, and we created a digital double for the Hera analog. And this is back when we took it out to the desert. We had a fully developed CAD model for that, and it was linked back to all of the functions in the habitat, such that you could essentially, it was possible in some cases to put on a set of virtual reality glasses, go inside and turn off lights and such like that. Currently, the technology allows, there's Melody mentioned the BIM model. You could probably talk about that later a little bit, but currently we have very rich CAD models, and they're also engineering-based modeling that uses SysML and things like that. So, yes. So we're slowly getting towards bringing all the models together, such that the eventual goal will, of course, to be able to build the model. The model will be completely functional, similar to how the actual artifact will be, and then you can actually control the hardware using that rich model. But we're not there yet. it's slowly getting there.
Is that a good answer?
Yes. What are some of the limiting factors that are slowing you down, would you say?
Yeah, it's very complex. Like for instance, I work a lot with both the CAD side and the SysML side.
Okay, got it.
And trying to link the two is very difficult, and it'll take a lot of little applications piled up on each other until we actually get to the point where that's possible. Bringing there's several other like SysML type applications that are working really well. For instance, National Instruments has a way of diagram, or MATLAB Simulink. So there's a bunch of similar ones that have their strengths and stuff like that. The National Instruments version, you actually get on and control motors and things like that. Simulink has its own strengths and weaknesses, and for the SysML, we're using Magic Draw, Cameo, but eventually all those strengths are going to coalesce into some kind of integrated model that will allow you to run the manufacturing of the parts, and then which goes all the way through. It's so rich that you can manufacture all the parts off of that model, and then later on, of course, control the model as well. But we're not quite there yet.
Thank you.
Melody, you would like to?
Sure. Sorry. I can jump in. I completely agree with Scott. We're not quite there yet. The truth is that digital twins are extremely valuable and extremely, let's say, interesting from a research perspective for a very long time, but creating a feedback loop between as-built structures, both buildings and construction as well as spacecraft, is very, very difficult. So digital twins, building information models, extremely valuable when you're still working in like a software-based space and not necessarily leading towards and not necessarily working with as-built structures as they're operational. So, but then as soon as the thing is built, yeah, the feedback loop is the tricky thing. So yeah, in the design space, I would say that it makes total sense to be working digitally, to be developing simulations and doing those kinds of systems engineering tasks within that digital twin. And then you can use that, or at least the way that we're approaching our work right now in construction is to use that model for procurement and other matters having to do with fabrication and manufacturing, which of course is the best way to get accurate information relative to pricing, costing, and then like your manufacturing needs. But then once the thing is built, how are you actually tracking metrics relative to what was put together and what was actually done? And how can you use that to generate data that would inform changes in the future? I think it's a really, really relevant question, both to terrestrial architecture, but also to spacecraft and vehicle design too.
Olga?
Well, yeah, I can add. So I see Vittorio also raise his hand because he is the one who is running now virtual reality and mixed reality lab and building it right now. I've finished building it at SIGSA. The major thing, of course, the difference is gravity gradient. And that's the major thing that none of analogs on Earth can replicate. And perhaps digital involving virtual reality and especially mixed reality capabilities brings us as close as possible to do that. Still, we just want to trick our brains as much as possible when we recreate these conditions. I think the major thing is, of course, with virtual reality is bringing it, make it interactive and connecting it with physical objects and subjects as much as possible, so we can test operational procedures as well. So that's something next step, and that's what we're trying to achieve. I don't know, Victoria, you want to add something?
Yeah, can you hear me?
Yes.
So I think that about I wanted to go back a bit towards like Melody said about the digital twin, and I think there is it's an incredible tool, yes, also for space architecture. And I think there is a very interesting concept that I read one time that was involving this idea of the digital twin for space applications. That at a certain level, because what we do is basically in the industry 4.0, we use digital twins and with sensors that are embedded in the real building. So the digital twin will also act like in the case of the industry, for example, it will like the production line will be will act exactly as the real one, because it's like getting real-time data from the production line. So the digital model will behave exactly like the real model. In space application, and this is very helpful because in the industry we learned that this is a tool to make extremely powerful and very like adherent to the reality provisional models in which we can forecast what will happen because we have so much data that are embedded in the model, and this data, they come from real sensor, that every single part of information that's come from the sensor that it's embedded in the digital model contribute to create an engineering model that's help us understanding, for example, things like the failure points or like the life of a certain component. So I was reading about this concept that was basically saying that at a certain level, through like advancements in machine learning and deep learning, we will be able to overcome the delay, the time delay between our buildings on Mars and the ones on Earth, because with time, the sensors will build an extremely accurate provisional model of what will happen in those buildings. And I think like that's now, especially the last developments that we are experiencing with machine learning and deep learning algorithms. I don't want to call them AI because it's not AI in a certain way. I think that like it can can have the digital twin as a concept, making like this next step over like what we are using it just right now. So like to implement completely new capabilities that will be like that we still can't foresee. I mean, I know that was not very clear probably, but
yes, I think that's very interesting. I have one additional remark about the procedures and decision making. I assume decision making on space habitat design has not been made by architects, but by managers, right? I'm asking also Melody, who is making, when you showed us the designs, you are the architect, but somebody has decided to do something else. And that was probably not an architect.
No, it certainly was not an architect. I can only speak to my own experience relative to the AAA analog, right? It was fully outside of the scope of the of the program to maintain a consistent vision between exterior and interior. In fact, some of the requirements relative to the interior programming and the actual, like even the hardware that the crew members would be using and how the space would be, interior space would be functioning, was largely undeveloped. So we kept asking for requirements. What's happening here? What are the crew members going to be doing? What is their schedule? And none of it was being shared. There was a lack of information provided, right? So we could only do as much as we could with the requirements that were given. And then beyond that, there was a clear division of scope within our contract. And despite, and I'll say this, like, despite even willing to do work in kind, provide furniture in kind, create millwork that would all be in kind, there was so much resistance to aligning on a vision which there was not much consensus around, because it felt decorative to certain program managers, and it felt non-essential to other program managers. And it was very difficult to maintain an argument for why a coherent vision of architectural interiors might be of benefit. I advocated for that avidly. I don't think there would be lazy boys on Mars, and I'm sure that people who have thought seriously about this problem see that as a missed opportunity. And so, you know, I personally think that there's, in the future, I mentioned this in my presentation, it's not every so often that we have multi-million-dollar structures and research analogs of this sort built. But what a missed opportunity to have synthesized input from a variety of disciplines, backgrounds, subject matter experts, both in like anthropology, philosophy, so many disciplines. None of that was taken into account. Bottom line, we had a budget to meet and a timeline to deliver on, which we did. But there was so much added value that I think we should be thinking about for future projects.
Well, Sandra, let me speak a little bit to that. We can't keep on blaming the system. Nothing is going to be perfect in terms of getting, let's say, a habitat to orbit. What, in terms of my retracing the development, initially we were encouraged with the precursors to ISS to have separate habitat module. Since that time, many other designs have only been able to separate the habitat functions from the laboratory functions within the same module. That's as good as we can do. But assuming you have a separate module, and I'll go back to some of the comments that I saw up there, don't discount management from having vision. Yes, some do. Who's on the top of SpaceX? I mean, there is vision out there, and part of our job is maybe to inspire to be, you know, a manager, you know, that we can do that. And I was a hab module manager for Boeing, and somehow they caved into that. Now, I can't say those were the best days of my life. It was terrible sitting in these management meetings, and just like you're saying, Melody, it's cost, schedule, budget. It wasn't the solution. It was those particular metrics. But still, if we want to get it done, we're going to have to do that. And, you know, we can't lose the vision, but there's a process there that's going to be pretty ugly in order to get there.
Bob, Sandra, Bob Blinkow here is a question.
Hi, it was John Blinkow, Gateway Spaceport. We're into space construction. We build the things that you guys design. And I have a question for Brand. You're working for Genesis Engineering, and tools are what we do, space construction tools. You're developing a pod right now, and I'm very excited about that because that's one of the things that we need. Is there a follow-on pod to what you guys are doing that's more tuned towards heavy-duty construction for space?
Well, that could be used. He's referring to a single-person spacecraft at Genesis we're developing. We put a lot of R&D funds into it. But that
can be used for construction, either piloted or teleoperated. You know, if some tasks are too hazardous or maybe pyrotechnic that you're uncertain of, you send that out. And we also have schemed up a two-person spacecraft, only because others have kind of said, what about two people? But, you know, a single-person spacecraft for the weightless environment is coming. It's coming. And we've talked a lot about EVA and, you know, the things associated with it. And I love suits. I've designed a suit, and even with, you know, talking about Mark's comments, and I flew on the KC-135 doing rear entry, not necessarily a suit port concept, but, you know, you maintain the structural integrity of the suit, and then you get in and out. The current suit, you have to break it apart, you know, so that's a good solution. But for the weightless environment, these single-person spacecrafts are coming. I just would like to see an American flag on them.
We need them for construction.
Yeah.
When it comes to moving heavy loads around, we need something bigger though, with a longer fuel duration. And I would, if you guys have work coming down the line for something bigger, especially that two-person variation you're talking about, I would love to see more on that.
Yeah, they did move 2 satellites. You know, that was the purpose early on of the manned maneuvering unit, you know, to be able to do it. But with our propulsion systems, they're pretty weak.
Yeah.
We'd have to find something else in order to do that.
Yeah. Thank you.
Thank you very much. I'm sorry, but I got some messages. We have to move on. Barbara had a comment. You want to?
I can tie it into my presentation, so I save some time.
Wonderful. I think that would be great. It's a great discussion, but I think we really have to move on. Session 2 is in Alma's hands. So I say goodbye from my session, and welcome Alma for the next.
Thank you.
Will you stay on, Sandra, or is it good night?
No, I stay on for a little bit longer, and then I will leave quietly.
Great. Okay, Alma, I think you're taking over the relay here.
Yes, I am. Yes. Hello,
Bye,
everyone.
bye, everybody. Bye.
Bye.
Bye-bye.
Ciao, Maria. Ciao.
Bye.
Hello, everyone. Welcome to the session 2. I would like to introduce Dr. Barbara Imhoff. Dr. Barbara Imhoff is an internationally active space architect and design researcher. She is a co-founder and co-managing director of Liquefier Vienna Bremen. Barbara Imhoff has taught at various renowned universities, such as ETH in Zurich, Chalmers University in Gothenburg, University of Kassel, the Berlin Weissensee School of Art, the University of Applied Arts, and University of Technology in Vienna. Barbara, the floor is yours.
Thanks, Alma, for the introduction. I'm going to share my screen now. Hope you can hear me well.
Yes, we can.
We can hear you well, Barbara, and I want to say hello to you as well. Good to see you.
Hi, Madam, and hi, everybody else. Lots of known faces and people. Yeah, I'd like to sort of talk a little bit about our work, some older and more recent projects, and it was great to hear Maria, who sort of paved the way into what I'm going to talk about now. I'd also like to actually start with, for Liquefier, we are sort of an interdisciplinary team comprising architects, designers, engineers, and scientists. And to us, you know, working in the space industry, which we have been doing for 20 years now, this kind of vicinity to collaboration with engineers is quite important, because, and now I sort of make a comment to the panel, because in reality in space, it's the roles are a little bit reversed. While, you know, houses on Earth, not all of the times I have to say, but sometimes or most of the times get sort of planned by an architect or architecture collaboration office, and the whole building is sort of orchestrated through this view and this lens, with the sort of the HVAC engineers contributing to it. The role in for space is reversed, because we have to establish this biosphere, and there are many other really stringent constraints we need to adhere to. So I think the interesting part is that architects, have a different role, and maybe that is why sometimes one has the feeling that the engineering takes over. But in general, the field of space architecture has been evolving and has found a larger voice than had ever before, I have to say. And with this, I start into the first project. It is sort of the gateway project we are involved in, particularly in the IHAB, the International Habitat Module, which is one of the core modules. Gateway, as you know, will be sort of a very small international space station comprising participation of NASA, ESA, JAXA, and the Canadian Space Agency, and possibly other partners. And while you might think, oh, it's just a small ISS somewhere around the moon, one has to consider that it's 1,000 times further away from the ISS, and therefore it is really a more extreme and harsh environment, and it's a very difficult place to build. That's also what we are seeing now in our collaboration with Thales Alenia Space in Turin, where Maria Antonetta comes from. So the Habitat module, now this is an older version which I can share with you, which we did for Airbus and with Thales Alenia Space. So you see it's an all-in-one module. It's this version has nearly 4 meters diameter. The current version, as Maria mentioned, has only 3 meters diameter. So it houses 4 crew members up to a mission duration of 1 month. And so one module has to incorporate all different systems, from private crew quarters, social gathering, and science equipment, but also other equipment. This is part of the food warmer and water dispenser for the galley. Then of course we need to think about the trash. Here is the sort of the gathering, the table. Previously we had an exercise device that has gone, but there will be still 4 crew quarters, which are important to sort of describe or have, provide a private sphere for the crew members. The toilet also now in this version, the latest version, has moved to another module just due to spatial constraints. There will be some small science equipments, but a little bit less than it is foreseen here. What can be seen and what is true for a space module is that the systems, the ECLAS, which has actually to be doubled as a backup, takes quite a lot of space. So you can see that there is spatial limitation, and we as architects, we are using design approaches and methodologies lying in transformability, deployability, to create different uses of space, and to allow also to stow away functionalities which are not needed the whole time, by the crew quarters are also deployable. So how to approach, I think somebody mentioned it earlier, how to approach a design that is through models and mock-ups. So this was the first mock-up built by Airbus, which was sort of a very simple, I would say, demonstrator where one could see what the spatial, how the overall size is, the spatial orientation, and the sort of the configuration. Everything was modular and could be exchanged. So the next step when we started to work for Thales Alenia Space was to sort of create demonstrators for specific parts. For example, you see here Alexander Gerst. This is from his private public Flickr account, I would say, private photo or ESA photo. And you see here when you look at so this was the old configuration, the overall module, and then the new configuration. You already see that here on that ring, on that silver ring, that this is sort of represents the small size of the actual module. So you have to, it's half of it more or less. So you have to imagine how much smaller it got from the first phase, A, B, so concept phase, to now the implementation phase. That has to do with our launch and transport capabilities. And so these mock-ups, you can see if again, how the volumetric, the volumes, how is it usable, what needs to be changed, the simple things. And currently we are preparing a mock-up for the critical design review, which will be sort of even more next phase, next step of realism. This is the so-called space mock-up. It also incorporates other demonstrators, which can be used for other, or which are sort of products for other uses. Gateway is to really provide access to the lunar surface, and in the far future, we do imagine living on the moon or having a larger moon village. So the Regolite project is from a couple of years back, and it had the premise of using a solar array that could be or solar arrays that could be concentrated onto a bed of lunar regolith, and three-dimensional elements could be sintered to protect the habitats, the pressure volume from micrometeoroids and from radiation, which is actually also a great challenge on Gateway, but it's also a challenge on the moon, especially for longer stays. So we created 3 setups. This is just showing one, which basically shows how this sintering process works. So that there is a solar array, or this is sort of a simulant of a lunar light, xenon lights. It's a laboratory setup, is being sort of projected through a mirror onto a movable table. It could also be through a Fresnel lens with real solar rays, and then layer by layer is sintered into elements. More recently, last year, we finished another multi-year study on taking that further, but looking not only at 3-dimensional interlocking elements, but also at 2.5D elements for paving, the sort of more paving elements. And what you can also see here, that the sintering, that it's done with a laser spot, which sort of simulates the sunlight, the concentrated sunlight. It's a 5-centimeter laser spot, and it's going a little bit further than just sintering. It's actually melting, but we could achieve quite large forms. So one of these forms is approximately 40 centimeters. So that's like 2 hand spans basically in width, and is sort of 2 to 3 centimeters thick. That's I would say 2 thumbs thick, not used to the metric system. So that could be also a technology which could be explored further. All these technologies are currently at a readiness level of 5 or 6. So there needs to be a lot of tuning to be really ready for a lunar within the base. Interestingly enough, this sintering technology has been around since the early 1990s, and it can also be probably used on Earth. This is part of this photo is taken from an island in Tonga Tonga in the South Pacific, which I took the photo when I was part of the artist expedition, actually. And this is also a special island. It does not exist anymore. It sunk 2 years ago, again, after it had emerged 3 years previously in 2015. But NASA took interest of that because it was sort of a new island, a new piece of land, and they studied how life can evolve, and also wanted to overlay that with probably extraterrestrial surfaces. I show this because we did a very, I would say, crude but interesting experiment to use a Fresnel lens to simulate solar sintering. I would say with the sand which was at the location. But that probably I would say is a promising start into maybe a technology that could be also used for terrestrial applications. The same is true for the Eden ISS greenhouse, which now after 4 years in Antarctica next to the Norway station returns home, first to the German Aerospace Center in Bremen, and then further to the lunar facility at the ESA Astronaut Center in Cologne. And as many projects, this project was also a multi-partner project with 14 partners under the lead of the German Aerospace Center. And you see here the Gardener Paul Zabe from the DLR harvesting was a special project because, or a special plant growth area because it used aeroponics. So the roots are sort of in the air. You don't need soil, you don't need a lot of water, you just need to spray the roots, and you can harvest on a 10 square meter area up to 270 kilos of vegetables, that is without the biomass you don't eat, within 9 months. So the overwintering period for the Norway station was, the food was supplemented by, during the overwintering seasons in 2018, was supplemented with a lot of fresh food, which really contributed to the mood and the spirit of the crew. So that is another part of technology, which is, I would say, of dual use to further develop for space and probably also for Earth. Here we have talked about suit ports a lot. This is the Moonwalk project, and it was about human-robot collaboration and to study how we can explore unknown terrain with a small helper rover, and to compare how it is different to two humans exploring together. But and you can see here also that we used our SHE habitat, our self-deployable habitat for extreme environments, for the mission control in Mars. Mars was Rio Tinto in the south of Spain, and ESA established analog. And what you also see, I just want to point out that simulation suit port. So the suit you see has a backpack that opens, so you can sort of backwards dock to these two open doors, and then you really need to sort of be quite strong with your arms, because then after the suit port or the backpack is open, you have to lift yourself up and backwards into the habitat. And while this is of course a very simple way of simulation, you know, when the backpack, even if when the backpack is a little bit bigger, you have to somehow lift yourself backwards into the habitat. It can be done. It's not that difficult, but it has to be trained. And here is sort of the human-human collaboration and the comparison. This project sort of goes a little bit further. It was also about 3D printing using lava, so molten regolith filled into molds and sort of slowly built up into these shapes. It was from the Astronaut Center in Cologne, a suggestion from who also worked very closely with the German Aerospace Center next to it. So it was the technology was a suggestion from the engineers working there. And going to Mars is really a very challenging endeavor. And I'd just like to point out that we will succeed in doing that, when we have, of course, sufficient transportation and we have mastered the radiation problem between sort of Earth and Mars. But also, and that is an interesting part that has been demonstrated, the advances here in our first session, for example, by Melody. We will need automated construction, but we also need sort of, because it will be all directed, even for the moon from Earth, we will not go there and build ourselves. So we also need an interaction between smart systems that, different rovers, different machines that can be, that can actually intelligently construct such a base in a very far away place. We need fully closed loop life support system technologies. One part, of course, is a greenhouse, but there's also other parts. And because of the sort of the restricted space, we will also need to look at specific parameters of how to use this space in an economically good way. So maybe these deployable or transformable or multifunctional structures. And we probably will also need to advance human performance, maybe also in that sense, to look at the pharmacological side and with regard to radiation protection. And all of these sort of 5 topics, and probably many more, they're also quite relevant for our life on Earth. And this is the topic of our next workshop. I just briefly want to announce, which we will run as part of the School of Disruption with the International Space University, with Search, with ESA, with ISU. Also Maria Perino will be participating, and the TU Delft. And well, if you're interested, please contact me, Liquifer, or the School of Disruption directly. Thank you.
Thank you very much. All right. Do we have any questions? I think we have in Q&A, there's a question from Steve. He says, he asks, which space agency has the led to build the gateway? Are they on track for cost and schedule to meet the deadline? And is the launch date scheduled for 2025 or 2026?
Sorry, can you, the first question?
You can see it
part of that question.
In Q&A, if you open the Q&A right there on the bottom, you can see the question.
But I can... is leading the gateway efforts, and there has been some delays, but I think it's not it's less than usual, I would say. It's they will start building it slowly, so the IHAB is sort of comes after the sort of the main propulsion module, and I don't, also the different parts they have changed a little bit, but it's not, I don't think it's 2026, it's probably 1 or 2 years later.
All right, okay, thank you. Do we have a question from the audience in the library?
I do, Alma, and this
Yes,
is all
please.
for our panel. Oh, there. Scott, Brand, there's a question for all of you as well. Barbara, we know that you're an architect, and can you tell us a little bit about your interactions with both engineers, but specifically with industrial designers, Barbara? Because there is, if Mark Cohen is listening in too, he may want to address this. There is a distinct educational difference in the industrial design curriculum and the architectural curriculum. And it's my biased opinion that engineers tend to hang around industrial designers more when you get to building or manufacturing components. I'm sure Brand will have something to say.
Was this a question, Madhu, or is this a comment?
In fact, maybe in the answer, I could clarify the question. I don't know if you can do that. But that I think Madhu was looking at what I consider the characteristics that differentiate engineers from industrial designers, from architects, and space architects are even a different breed. But regardless, I find some engineers to be pretty creative. You know, they don't stay within their discipline. And then I find some architects that aren't very good designers, actually. Industrial designers, that's what it's supposed to be. But usually it takes a very special industrial designer, I think, to contribute to the space environment. They tend to be, I think, more on visual products than they do on, let's say, the functionality of it. My experience being hired in by an engineer, Gordon Woodcock at Boeing, was you advance ideas because there's not clear direction. And, you know, that's how you progress, is that, you know, you're not going to wait for something that says, okay, here's your work assignment. You just take the initiative, and then if it's wrong, it's wrong, but that helps you move on. And, you know, in some cases, you need to argue your way into, you know, being able to have that design surface. Other times it's going to get shot down for all the right reasons. And, you know, we put too much ego into what we're doing. I've found a pretty safe approach is to develop alternatives within your own design set. Yeah. You know, don't fall in love with one of them, but develop those alternatives. It's very healthy, and be able to, you know, move those forward. But you know, I've had great relationships with engineers and being able to do it. Their job, though, is to quantify. Yeah. If you don't quantify it, you're not doing engineering, right? That's right. Okay. Then in terms of architecture, we've got to maintain the vision. And we got to, it's like designing a house or anything else. You got to have that vision up front and maintain that vision. But if you find out you can't do it, then back off and come up with some other clever solutions. Now, I don't know if I've answered the question, but that's basically what
kind of. But I want Barbara's thoughts on an architectural education versus an industrial design education, and maybe Scott here will also add to it, but please.
Okay, so I have to maybe say that I graduated from an art academy in architecture. So at the beginning, I remember being at Johnson Space Center. It was a culture shock, not because it was Texas, but it was sort of a very different design environment. And I I'm not so, Madhu, I don't know if I can say, what the designers do in respect to the engineers. Maybe, you have a point here, but what I'd really like to stress is I think that every profession, if it is, a lawyer, an accountant, a medical doctor, or an engineer, or an architect, designer, they're all creative in their own ways. Some are more than others, and there's always a potential to also keep a vision. So I think that is what we need to keep in mind. And I have been learning a lot from engineers, from the space engineers. And it's sort of vital to learn their language, to understand, how they think, and maybe also find a way to explain or sort of common ground, establish common ground where one can design collaboratively and together. I think the creativity is really in, it can be in any kind of area. It is really up to the people to sort of also, harness that, what they have in them.
Scott?
Yeah, so my experience is slightly different from, say, brands, where I've seen a lot of industrial designers who they get really a lot of education into manufacturing and things like that for the product that they're trying to work on. Whereas there's a lot of architects who just like to paint facades and do things like that, where they have no idea what's going on behind the structure. They say, "Oh, let the engineer do that." The one interesting thing that I've seen since I've been into NASA is that the engineers like to start with requirements. And if they have a list of requirements, then they can start to work on their thing. Whereas architects start with a blank white page. And I think this is the kind of philosophy that we had when we were doing the HDU or what is now the HERA, is that we started off with a blank page, and as we were going along, our philosophy was, well, we're building something so that we can derive requirements out of it. And a lot of the things that we did, we had a cycle. It was a 6-month cycle for subsystems and a 1-year cycle for the habitat itself. And as we went along, we realized that, well, this is not going to work. We're going to have to, the requirement that's coming out of this is not what the requirement is going to need to be for the final thing. And so we ended up doing a lot of changes. But we didn't start with the requirements. We started with the blank page, and we started to derive those requirements out of that later.
Good point.
But Scott, I want to stay there. I really want to know, because I'm not sure if it's really a blank page, because we have always something in our mind, what we need to achieve. And so, I think we also start with the requirements. We just don't, set it up in the same way. And if you do a building, you look at the site, you have all these kind of, environmental requirements.
Barbara is beating around the bush to say that she has a concept, vision.
Yes, you're right. Because if you say it's a blank page, well, is it going to be an airplane? Is it going to be a fork? So you're right. There is kind of a vague set of requirements that are there that you kind of have in the back of your mind, but it's not something that like the engineers need. Like Brand was saying, you have to converge on a number.
But I think architects should take should feel good about this, because I was trained under an engineer who told me that the best requirements are written after the design and execution of the mission, and this is true.
Yeah, I think there's one other point we never talk about it, but it's aesthetics.
That's right.
And I think that is quite different, because that is part of an architecture education, and so this is something which doesn't appear too much in the engineering world. I guess. It's not that people are not trying to, they all have their sense of aesthetics, but I think there's the way people, we are trained in that, or we also talk about that, or we are lectured in that. That is very different.
Absolutely. That's why satellites look ugly. Just kidding. Okay, good.
Thank you very much. We should really proceed forward. Barbara, thank you very much for your lecture. It was really nice and interesting. And let me introduce Dr. Olga Banova.
Thank you. Thank you, Barbara.
Thank you, Barbara.
Thank you.
Hello. Dr. Olga Banova is a research professor at the University of Houston's Cullen College of Engineering, director of the world's only Master of Science in Space Architecture program and Sasakawa International Center for Space Architecture. Olga conducts research and design studies of orbital and surface habitats and settlements, including inflatable structures, special design influences and requirements for different gravity conditions in space, and habitat concepts for extreme environments on Earth. Olga, the floor is yours.
Thank you, Alma. Very impressive how you just read it all. Usually some people stumble over this, especially Sasakawa. Okay, thanks very much. Thank you. Good. Thank you very much, everyone, for sticking around for that late. I'm very impressed. So I am, as we proceed, I'm trying to make it less and less slides. So I would prefer to have a discussion if it's possible after at least some time. So the title of my presentation is Reality Check. And so that's what I thought is really important, to see how we can connect with the industry and with the future needs or needs for future space exploration that we have been discussing quite a lot during all these previous presentations. And by the way, continuing to the previous discussion and about creativity, I'm 100% agree with Barbara that creativity is not defined by the discipline or by the special skills. Creativity comes with in all different ways from different directions, and that's why architecture is a great discipline, because ideally it's trans and multidisciplinary discipline itself, because we need to think about all the aspects, technical, social, everything what comes from human side, everything what comes from environmental side, everything what comes from engineering, and connecting it all in the most efficient and best possible way that will serve the purpose. And the purpose is to serve people. So that's why space architecture in general then even exists, or I think, and why it's needed. Again, as I said, motivation comes from desire to enable the exploration of new worlds in most satisfactory way, I would say. So we don't want to lose lives. We don't want to damage environment. We want to do it in the most enjoyable way, if you will. So it's, again, architecture organizes and interprets the creation and enrichment of built environments, and it's quite broad, because whatever we build, it's not only for necessarily human living in it, but as soon as humans will operate it, interact with it, it has to be designed in such a way that it becomes part of overall architecture, either it's in space, in orbit, flying to distant worlds, or on surface of Moon or Mars or elsewhere. The thing is why space architecture is more probably demanding than terrestrial architecture, let's say, because we do need to have at least some understanding and knowledge about more things that terrestrial architects do. Need to think about orbital mechanics, what is propulsion is, and how much that has to be part of our overall architecture. If we're talking about spacecraft design that goes somewhere in space, I need to think about different gravity conditions, protecting humans, and psychology of living in an enclosed and isolated environment for quite some time with very limited number of people. Any other topics, very many other disciplines that are connected to that. And other fields, of course, we're connecting with aerospace engineering, we're working with them. We're not, we should be partners. And it's important to respect everybody's desire to design in the best possible way. And understanding of that can be different. But that's when real creativity happens, because then we really can enrich each other's experience and make probably better, or find a better solution for design and future unknown conditions. Again, law, and the end is law and art is part of it, because that at some point will become also one of the, or part of the requirements. And as I'm talking especially about law, all these regulations and the ways how it could be designed, if we're talking about surface of the moon, for example, different agencies, different countries, different companies building and developing different infrastructures there. So that will be important for architects at least to understand and listen to that. And art comes from different ways in different forms, not necessarily and not even at the least maybe that's a picture or paintings on the wall, but more integrated into living and working of the crew of people, and again insulated environment for a long period of time, the way how we can make their life more enjoyable and more productive. So that's how we'll look at it. Again, who are our clients? Architects is always about architecture, it's always about clients and working with clients, satisfying their needs and requirements on Earth, and the same in space. This is combination of working with needs that agencies or corporate companies need from us, and what they need and what they expect, and also those who will be using those environments, those architectures. Understanding it and talking to them, seeing the environment, seeing the criticality of certain design decisions from their lenses is very important. I saw in the comments Esther's talking about her experience, talking about Cristoforetti astronaut, and about the habitability and how she was appreciative or very concerned about architectures. That's exactly what we need to do, and listen more. Again, next missions, next long-term and sustainable presence on the moon will require large number, or at least repeated visiting from researchers and scientists who will be establishing ISRU plans, or technicians who will be overseeing those activities. So this different group of people that haven't been dealt with when designing for space. When we're talking about space missions on the ISS, for example, it was quite different, the group of people who visited the ISS so far. Well, again, the general thing is milestones of space mission planning. And I know that planning, space mission planning, usually is taken care of way beyond the level of engineers and architects. It's on a higher level of agencies or companies and so far. But we need to know, we need to be part of these discussions and these conversations. because you cannot design in an element habitable space, habitable volume, even more if we're talking about settlements and bases, without understanding overall needs, goals, and objectives at every stage of the development. So involvement of architects, involvement of engineers together with architects at this very starting point of mission planning is important. Also, of course, thinking about and knowing what are the launch capabilities, what kind of propulsion systems will be needed to reach, to go somewhere to Mars, for example, what kind of power systems and so on. All these considerations affecting and are different for different missions. So missions can vary from tourism to just servicing and maintaining a station of spacecraft in orbit. Those have to be addressed from different perspectives, and this affects also the way how habitable spaces will be designed, how we will arrange the zoning inside, what kind of functions will be present. That's everything is depending on what are the mission goals and objectives, what we need to serve. Again, the ways how we validate our design decisions, our designs, here comes all this discussion that we were talking about digital twins and using VR and mixed reality. For that purpose, on Earth, we need to start evaluating our design decisions as soon as possible, from operational perspective especially. From operational perspective, also the level, not, for example, one crew member experiencing the design and performing a task, but when several crew members, or as many as is supposed to be on the mission, interact with each other in the given environment. Again, the challenges, talked about it a lot, so I probably won't stay here very long. Because the great launch mass and volume constraints, it's again pretty obvious that we need to launch everything from Earth. We have restrictions of the volume, the mass that we need to, we can put our payload in. We need to design to prevent the crew being harmed by all the hazards presented in space and its vacuum, radiation, then it's extreme temperatures, again, microgravity and partial gravity. We still need to take care of physical health of the crew. Talking about planetary surface difficulties, they still need to deal with gravity, microgravity, and we don't know how that will affect the crew. We only can assume certain things, but still need to provide all the means for the crew to stay healthy, how we protect crew and what kind of human factors support we can offer. Psychological, social, and cultural problems associated with isolation and confined environment as also very much drivers for design requirements as well. So all of these challenges actually then become our design requirements in addition to requirements coming from engineering side of it, engineering requirements. And of course, we need to protect the crew and make it safe for crew from all means. Gravity-related design considerations is more about, again, mitigation of physical health hazards, how we can do it. We need to provide visual cues in microgravity or zero gravity conditions, still probably be helpful, provide some, facilitate the circulation in partial gravity conditions. It may be better, but it may be worse. Something, it will be different from Earth for sure, and it will be different for the crew after a long duration flight in zero-G conditions. Where we store water and how we can distribute it, how we distribute all other needs, how we will run all the utilities inside the habitats, redundancy, what we can afford. We cannot afford redundancy in each module, probably. Have to be really, really frugal what we bring there. We also need to maximize safety, health, critical aspects, and probably always find a good compromise, what we can find, bringing there to support the crew, but also helping them with a larger volume. By the way, larger not necessarily better. Astronauts very often say that how the space is organized is more important than how it's big. Well, we know how big it is. We know right now on the ISS, it's still quite crowded space that they deal with. So that's organizational approach, how we can optimize the space in the best possible way is important. On the surface, in addition to other problems, need to think about dust protection, mitigation. We need to think how we can utilize ISRU resources the best possible way. Here comes, of course, 3D printing, getting resources from regoliths, for example, getting water in situ, getting oxygen and metals in situ. We still need to protect the crew from radiation hazards, but again, transportation as also will be needed with if it's pressurized rover or non-pressurized, what kind of EVAs we can support. All of that affects our design considerations. So with all that said, where is what our point? Where is our side? What kind of role space architecture can play? Again, in our design, in our program, usually that's the approach that students are offered to take is look at this, finding the gap in this, in the research, in the requirements, and in the approaches that is the space agencies doing right now, or other commercial activities proposed right now. So the space architecture design driver to find this current capabilities gap. For example, looking at this artificial gravity design, 400 tourists to go around the moon, that was designed at our Center for Bigelow Aerospace many years ago. It's even scary to say how many, more than 20 years ago. It's this grand design idea. This is big rotating vehicle. Two bigs on two sides. There are inflatable habitats that will support 100 people, 75 tourists, 25 crew. How we will get there? There is obvious gap, and perhaps if we're talking about artificial gravity, so maybe we need first to think how we can test this type of structures. We don't even know how systems will work. We don't know how fluid dynamics will be in a rotating. Well, we can guess, we can calculate it, but we need to test it first in zero-G conditions, not on Earth. Also, how people will adapt to in rotating environment. So here's one of the projects that one of the students did a couple of years ago, is starting small and figuring all of that out. So what if we use our capabilities that we have right now and see what we can do with that? So here's, he proposed that the pre-chow module, this Roscosmos module, that would attach to Progress and two Dragon capsules attached to this on tethers. And then it will start rotating. It first gets powered from the ISS, then it detaches from the ISS, and rotation begins, and then we can test these systems. And then we can have, also can have a subject, well, people in those Dragons, and see how people can adapt to in rotating environment, what they can do from operational point of view. Also, another example on the lunar surface, before we have such a big infrastructure on the surface. So what we can do, maybe we can start from that. And this project that we did for Boeing a couple years ago, designing a very small habitat that for crew of 4 for 2 weeks, that the crew will be, the major task would be for the crew to offload logistics cargo module, cargo from a lander into the habitat module. So we looked at different configurations, how we can do this stuff, what it will require. Before that, we looked at deployable, inflatable airlock options, again, minimizing it as much as possible and making it as light as possible. So inflatable airlock with just one hatch. Really, Boeing was interested in this option. That's what we suggested to use. Here is this comparison between these 3 types of airlocks. This was designed for zero gravity conditions. But on the surface, we suggested it can be used for cargo offloading and loading into habitats. So we have only one hatch, which makes it very, very light, as light as possible. We also looked at different levels of automation for unpressurized row for cargo delivery or to astronauts delivery. Different levels of automation defines different levels of automation and capabilities of the habitat. So it's all have to be evaluated. It's a lot of trade studies, and that's what space architecture is good about. And find the most economical and optimized way of design. So here's examples how interior can be reconfigured. Very, very tight environment, very limited. So what we can offer for the crew, exercising is just barely just a rubber band. That's what they will be stretching. Then hygiene is all deployable structures. When this habitat will have to be reconfigured, only 2 crews can be inside reconfiguring it. Other two will have to step out in this crewed airlock outside, which is not the best solution. Okay, so what is our goal? What we need to look into to design? What are the big scale requirements and to satisfy the client, and what the clients usually need? They want to be, of course, their efforts profitable, if we're talking about agencies or especially private companies. Aesthetics is one of the functions. It has to be aesthetically not only pleasant, but it's aesthetically satisfying. Still, it has to be very practical and flexible. Flexibility of the design allows easy adaptation to different mission needs or crew needs. It also allows adapting it to different technological needs. So that's also important to allow the habitat systems, allow these habitable spaces to be adjustable to new capabilities, technological capabilities. So value-based design is somewhere in the middle between feasibility, space optimization, and the function, satisfaction of the function. So here's to remind you what is right now going on and where our graduates are working now. So it's in Axiom, as you know, working on this commercial orbital station. Doing quite well, so we will be visiting them soon with this class. And other 3 is Blue Origins and NanoRax and Northrop Grumman, all proposed their stations, and all of this on the development right now. So that's super exciting and super nice. So thank you. And again, so the graduate program, if somebody doesn't know what we offer at the University of Houston and the College of Engineering is two types of Master of Science programs and degrees. So it's one in Master of Science in Space Architecture and another is dual degree with Aerospace Engineering and Space Architecture. So thank you very much. If you have questions, I can answer some questions.
Thank you very much, Olga. Thank you. Do we have some questions from the audience?
Questions? Yes. Yes, we do.
Hello, my name is Claire. I was wondering, so you had a slide on stakeholders who are interested in the space architecture. Who do you think besides governments like NASA and ESA would be funding the opening market for that kind of space architecture space?
Well, those companies that I showed this in the end, so 4 commercial stations now it works. So Axiom is a little bit ahead. So they pursue 2 types of commercial activities, tourism, of course, and research. Research and potentially production. A lot of the research is related to medical and pharmaceutical activities and companies. So I know that many years ago, the company that Larry Bell and Guy Trotti organized the space industry. So they actually thought that pharmaceutical companies would be interested and they tried to start business based on that. They didn't get much of interest, but that was 30 years ago. So it's quite different now, more and more medical and medical activities happening there. And the ISS is very busy with research really related to healthcare and drug delivery and smart drug delivery. And that can be done in 0G only, that kind of activity development. So that's probably, did I answer your question?
Yeah, definitely. Thank you.
Thank you very much. We have another question from Amel. He says that he has a bachelor's in architecture. Can I get into the dual degree program?
Well, that will require to satisfy prerequisites. And those prerequisites are coming from some classes in mechanical engineering, which is, I have few students who actually took that path. And they fulfilled, so it just took them longer, but they took these undergraduate classes. And one is about to graduate in 2 weeks, I guess, the end of the semester. So it will be longer, but yes, but you have to satisfy those requirements. So usually I suggest if somebody in the very beginning, their educational path asks what to do and what takes, I suggest to have a minor in engineering and take those at least courses that can be qualified as prerequisites. Solid dynamics, fluid dynamics, usual stuff. Nothing really special.
Perfect, thank you, and good luck to Amel.
Yes,
do we have more questions, or do we proceed?
Alma, Olga, you know, I commend you on the program and the way you tenaciously proceed with the agenda, because I know from our discussions that it is not easy to survive and exist